From the very first moment you began to count, from the first time you held up your fingers and matched them to the objects in front of you, you were touching something ancient and deep, something that existed long before anyone had a name for it. That act of counting, of matching one thing to one number, seems so natural that you might never stop to think of it as a human invention, but it was, in its way. Counting was a discovery, not of a thing that could be held or seen, but of a pattern that was always there, waiting in the silence of the world, waiting for someone to notice it. And once it was noticed, once the pattern of numbers began to unfold, it never stopped. It grew and it branched, and it twisted into shapes that no one could have predicted from the simple act of holding up 5 fingers and saying 5. Numbers, as you know them, are not the only way to count. In the ancient world, different cultures had different symbols, different words, different ways of grouping and carrying and trading. But the underlying structure was the same. 1 and 1 make 2. 2 and 2 make 4. 4 and 4 make 8. This is not a human law. This is not something that was agreed upon in a meeting or written down in a treaty. This is something that seems to be built into the fabric of anything that exists at all. If you have one stone and another stone, you have 2 stones. That is true whether you are in a city or on a mountain, whether you are alive now or whether you lived 10,000 years ago. The truth of it does not depend on you. It depends on nothing at all except the simple fact that there are stones and that they can be counted. This is the first quiet mystery of mathematics, and it is a mystery that never really goes away, no matter how advanced the equations become. The fact that numbers work, that they are reliable, that they behave the same way every single time, is something that people have simply come to expect. But if you stop and think about it, if you let the thought settle into you as you lie here in the dark, it is strange that the world should be so orderly. It is strange that 2 plus 2 always equals 4, no matter where you are, no matter what you are counting. There is a kind of faithfulness to numbers that you do not find in many other places. People change their minds, weather changes, the tides come and go, but numbers stay exactly where they are, waiting for you to come back to them, waiting for you to pay attention. What is even stranger, what is almost unsettling when you sit with it long enough, is that the orderliness of numbers is not something you or anyone else invented. It was always there. The pattern of counting was not written by human hands. It was written into the structure of existence itself, and all that humans did was learn to read it, slowly, carefully, over thousands of years. The first people to read that pattern did not have textbooks or calculators or computers. They had sticks and stones and their own 2 hands, and they noticed something that still holds true today, something that is so simple that a child can understand it, and so deep that the greatest mathematicians who have ever lived are still wrestling with it. They noticed that some numbers cannot be broken down any further. They noticed that there are numbers that are only divisible by themselves and by 1. They noticed the primes. You have known about prime numbers for a long time, probably since you were in school. 2, 3, 5, 7, 11, 13. These are numbers that stand alone, that resist being divided into smaller whole pieces. They are the atoms of the number system, the indivisible building blocks from which every other number is constructed. Every number you can think of, no matter how large, can be built out of primes. You can take 12 and break it down into 2 times 2 times 3. You can take 100 and break it down into 2 times 2 times 5 times 5. The primes are the foundation, the bedrock, the original material from which all of arithmetic is assembled. And yet, for all that they are the foundation, they are also among the most mysterious objects in all of mathematics. They are simple to define, they are hard to predict, they are everywhere, and they are nowhere. They are the most ordinary and the most extraordinary of numbers. Think about this for a moment, gently, without forcing the thought. The primes are the simplest possible numbers, the numbers that cannot be divided. You would think that such simple numbers would be easy to understand, easy to predict, easy to describe. But they are not. If you try to guess where the next prime will appear, you cannot. If you try to find a pattern in their spacing, you cannot. Sometimes they are close together, like 11 and 13, separated by only one number. Sometimes they are far apart, with long stretches of ordinary numbers between them. The gaps are irregular, unpredictable, almost random in their distribution. And yet, and this is the part that has kept mathematicians awake at night for more than 2,000 years, the primes are not random. They follow a rule, a law, a deep structure that is hidden from view. The rule is there, it must be there. But no one has ever been able to see it clearly enough to describe it in a way that satisfies the human mind. The ancient Greeks knew about this mystery. They were the first people in the Western tradition to think about mathematics as something more than a practical tool for counting and measuring. They saw mathematics as a form of truth, a pure and perfect truth that existed beyond the messy world of human affairs. And they took the primes seriously. A man named Euclid, living in the city of Alexandria around 300 years before the Common Era, was the one who first proved that the primes never run out. He showed, in a way that was so clear and so simple that you can still follow it today, that no matter how many primes you find, there is always another one waiting just beyond them. His proof is one of the most famous in all of mathematics, not because it is complicated, but because it is the opposite of complicated. It is simple, clean, and it has never been improved upon. It is exactly as true today as it was when he first wrote it down. Euclid's proof is worth understanding, not because you need to memorize it, but because it shows something important about how mathematics works. He imagined that you had gathered up every prime number that could possibly exist, a finite list, and he showed that you could always multiply all of them together, add one, and produce a new number that could not be divided by any prime on your list. That new number would have to be either prime itself, or it would have to be divisible by some prime that you had not included. Either way, your original list was incomplete. There would always be another prime beyond it. This is not a guess. This is not a pattern that seems to hold. This is a proof. It is guaranteed, forever, for all time, for every possible prime that has ever existed, or ever will exist. And it is beautiful in its simplicity. It is the kind of proof that makes you feel, for a moment, that you have touched something eternal, something that will still be true long after you are gone. But Euclid's proof, as satisfying as it is, does not tell you everything. It tells you that the primes are infinite. It does not tell you where they are. It does not tell you how to find them. It does not tell you whether there are patterns in their distribution. It gives you certainty that they exist forever, but it gives you no map of their territory. That gap, that difference between knowing something exists and knowing where to find it, is one of the central tensions in all of mathematics. It is the difference between knowing that there are stars in the sky and being able to predict exactly where a new star will appear. Euclid gave you the first part. The second part, the part about the pattern, remains unsolved. As you lie here, in the quiet of the night, it is worth letting that thought settle into you. There is a question about numbers, a question that is older than almost any other question in mathematics, and it still does not have a complete answer. The primes are infinite, you know that, but how are they arranged? Are they scattered at random? Is there a hidden pattern that no one has yet been able to see? These are not idle questions. They are questions that sit at the very heart of mathematics, and they have been sitting there for more than 2,000 years. Mathematicians have come and gone. Entire civilizations have risen and fallen. And still the primes keep their secret. The search for that secret began long before anyone thought to call it a search. It began with people like Euclid, people who looked at numbers and saw not just tools for counting, but objects of beauty and mystery. It continued through the centuries, through the Dark Ages and the Renaissance, through the Age of Exploration and the Age of Reason. Mathematicians in India, in the Islamic world, in China, in Europe, all contributed pieces to the puzzle. They discovered new properties of numbers, new ways of thinking about them, new connections that no one had ever seen before. And slowly, over the course of centuries, a picture began to emerge. It was not a complete picture, it was not even a clear picture, but it was enough to show that the primes were not random, They were following a rhythm, a deep and subtle rhythm that was tied to something far larger than themselves. One of the most important early hints came from a mathematician named Carl Friedrich Gauss, a man who is often considered the greatest mathematician of all time. Gauss was a prodigy, a child who could do complex calculations in his head before he was old enough to write. He spent much of his life studying numbers, not because he had to, but because he loved them. And one of the things he loved most was the primes. As a teenager, he began to look at tables of prime numbers, long columns of numbers that had been painstakingly compiled by people who had spent years checking each one by hand. He looked at these columns and he noticed something. He noticed that the number of primes below a certain value seemed to follow a simple rule. It was not exact. It was not a perfect formula, but it was close. The closer you looked, the closer it got. Gauss had found a pattern. The pattern that Gauss found is now called the prime number theorem. It says, roughly, that the number of primes below a very large number is approximately equal to that number divided by the natural logarithm of that number. If you do not know what a logarithm is, that is perfectly fine. The only thing you need to understand is that Gauss had found a way to guess, with remarkable accuracy, how many primes there are in any given range. He had not proven it. He had not explained why it worked. He had simply noticed that it seemed to be true, and he was right. His guess was correct. It was proven, independently, by two mathematicians in the 1890s, more than a century after Gauss first proposed it. But even that proof, as satisfying as it was, did not fully close the gap. It gave mathematicians a way to approximate the distribution of primes. It did not give them the exact distribution. It did not tell them where every single prime was located. It gave them a map, but it was a map with blurry edges. The blurriness mattered. Mathematicians wanted more than an approximation. They wanted certainty. They wanted to know the exact rhythm of the primes, not just the average rhythm. And that desire, that hunger for precision, led to one of the most remarkable discoveries in the entire history of mathematics. It led to the work of a man named Bernhard Riemann, a quiet, sickly German mathematician who lived a short life and published very few papers, but whose influence on mathematics has been immense. Riemann wrote a paper in 1859 that was only 8 pages long. 8 pages. That is not even a long chapter in a book, and yet those 8 pages changed mathematics forever. In that paper, Riemann took a function that had been studied for years, a function that had nothing to do with primes on the surface, and he showed that its behavior was intimately connected to the distribution of the primes. He showed that if you knew where the zeros of this function were located, you would know everything about the primes. You would know exactly how they were spaced. You would know every tiny irregularity. You would have the precise map that Gauss had only been able to approximate. The function Riemann studied is now called the Riemann zeta function. It is a kind of infinite sum, a sum that goes on forever, adding up smaller and smaller terms. It is not an easy thing to visualize, but you do not need to visualize it. You only need to understand its significance. Riemann noticed that the zeros of this function, the places where it equals exactly 0, seem to lie along a single straight line. He did not prove this. He simply noticed it. He mentioned it almost in passing, as if it were a minor observation. And that passing observation became one of the most famous unsolved problems in all of mathematics. It is called the Riemann Hypothesis, and it is the single most important open question in pure mathematics. The Riemann hypothesis says that all of the non-trivial zeros of the zeta function lie on a particular vertical line. If that is true, then mathematicians would have a complete understanding of the distribution of the primes. They would know exactly how the primes are arranged, down to the last detail. If it is false, then the primes are more complicated than anyone has ever suspected. Mathematicians have checked billions of zeros using computers, and every single one of them lies on that line. But checking billions of cases is not a proof. It is evidence, powerful evidence, but it is not certainty. A proof would be certainty. A proof would close the gap forever. No proof has been found. The Riemann hypothesis remains unproven, more than 160 years after Riemann first proposed it. There is something deeply humbling about this. Here is a problem that can be stated in a few sentences, a problem that has been worked on by the greatest minds in mathematics for more than a century, and it still resists all attempts at a solution. It is not that mathematicians have not tried. They have tried everything they can think of. They have built entire new branches of mathematics in the hope of solving it. And still it sits there, waiting. It is a reminder that human knowledge has limits, that there are things we do not know, and that some of those things may remain unknown for a very long time. It is also a reminder that the world is not simple. Even the simplest objects, the prime numbers, turn out to be connected to some of the most complex and subtle ideas in all of mathematics. The primes are not just numbers, they are a window into a deeper structure, a structure that we have only begun to glimpse. So as you settle further into the night, let this thought rest with you. There is a mystery at the heart of counting, a mystery that has been there since the first time someone picked up a stone and wondered how many they had. That mystery is not a failure, it is not a weakness. It is the opposite. It is a sign of how deep the world is, how much there is still to learn, how much beauty remains hidden beneath the surface of the ordinary. The primes are infinite, you know that. And yet their arrangement is a secret. That secret is not a problem to be solved. It is a fact to be lived with, a fact that gives mathematics its endless depth, its endless capacity to surprise and to teach. You do not need to solve it. You do not even need to understand it fully. You only need to know that it is there, quietly waiting, as reliable and as mysterious as the stars that will still be shining in the sky long after you have fallen asleep. Let your mind drift back now, back past the quiet hum of your phone, past the soft weight of the blankets, back to a time long before anyone had ever written down a number. Imagine a world where counting was not yet a system, where the only numbers were the ones you could hold in your hand, stones and shells and the fingers on your own two hands. The first people who began to count were not doing mathematics in the way you might think of it now. They were not trying to solve puzzles or prove theorems. They were simply trying to keep track of things. How many sheep had gone out to pasture in the morning? How many had returned at dusk? How many days had passed since the last full moon? Counting was a practical tool, a way of bringing order to the daily business of survival. But even in those earliest days, something else was happening, something that would eventually grow into the great questions that still occupy the minds of mathematicians tonight. The people who counted were noticing patterns. They were noticing that certain numbers seemed to appear again and again, that some numbers had a kind of wholeness to them, a completeness that others lacked. They did not yet have words for prime numbers. They did not yet know that these numbers would one day become the foundation of cryptography and the subject of some of the deepest unsolved problems in all of human thought. But they were already, without knowing it, standing at the edge of a mystery that would never fully be resolved. As you settle deeper into the night, it is worth thinking about how strange it is that something as simple as counting could lead to something as complex as the questions we have been exploring. Counting is the first mathematical act, the one that every child learns, the one that feels so natural that you might never stop to think about it at all. And yet from that one simple act, an entire universe of ideas has grown. The primes are the first mystery that counting reveals, the first hint that there is something hidden beneath the surface of the ordinary, something that does not reveal itself easily. The ancient Greeks were the first people to take this mystery seriously, to treat it not as a practical problem but as a question worthy of contemplation for its own sake. They were the first to understand that the primes were not just numbers that happened to be indivisible, but that they were the building blocks of all numbers, the atoms of arithmetic. They knew that every number, no matter how large, could be broken down into a product of primes, and that this breakdown was unique. No number could be built in two different ways from the same set of prime building blocks. This is a truth that feels obvious once you know it, but it is not obvious. It is something that had to be noticed, had to be proven. The Greeks proved it. They called it the fundamental theorem of arithmetic, and it is one of the most important results in all of mathematics. But even with this theorem, even with the certainty that every number is built from primes, the Greeks knew that they did not understand the primes themselves. They knew that the primes were infinite, thanks to Euclid's elegant proof. But they did not know how to find them. They did not know if there was a pattern to their distribution. They did not know if the gaps between them followed any rule. These were questions that seemed to be just beyond reach, questions that would remain unanswered for 2,000 years. The centuries that followed the Greeks were not empty of mathematical progress, far from it, but the questions that the Greeks had posed about the primes were largely left untouched. Mathematicians in India, in the Islamic world, in China, and later in Europe, built on the Greek foundation. They developed new tools, new ways of thinking about numbers, new methods of calculation. They solved problems that the Greeks could not have imagined. But the primes remained stubbornly mysterious. It was as if the primes had a secret, and that secret was not going to give itself up easily. There is a reason for this, and it is worth sitting with for a moment. The primes are not just any numbers. They are the simplest possible numbers, the numbers that cannot be divided. You would think that such simple numbers would be easy to understand, but the opposite is true. The simpler a thing is, the harder it can be to explain. The primes are so simple that they resist being broken down into anything else, and because they cannot be broken down, they cannot be understood in terms of anything simpler. They are the foundation, and a foundation cannot be explained by what it supports. It can only be observed, described, and eventually, if you are very patient, perhaps understood in its own terms. This is the great irony of the primes. They are the most basic things in arithmetic, and yet they are the least understood. They are the atoms, and the atoms, it turns out, are the hardest things to see clearly. You can build a house out of bricks, but understanding a single brick, really understanding it, is a different kind of problem. The primes are like that. They are the bricks, and the house is arithmetic. And for all the houses that have been built, the bricks themselves still hold secrets. The search for those secrets is the story of the next chapter of mathematics. It is the story of how people began to ask, not just what the primes were, but where they were. It is the story of how counting became something more than counting, how it became a way of asking deeper questions about the structure of the world. And it begins, as so many mathematical stories do, with a man who could not stop looking at numbers. Carl Friedrich Gauss was born in Germany in 1777, and he was one of those rare people who seemed to see mathematics everywhere. He was a prodigy, a child who could calculate complex sums in his head before he could read. He grew up to become one of the most influential mathematicians who ever lived, and one of the things he loved most was the primes. He spent hours, days, years, looking at tables of prime numbers, long columns of them, compiled painstakingly by hand by people who had dedicated their lives to the task. Gauss looked at these tables, and he saw something that no one had ever seen before. He saw a pattern. The pattern was not exact. It was not a formula that could predict the next prime with perfect accuracy. It was something more subtle. Gauss noticed that the number of primes below a certain value seemed to follow a simple rule. The rule was not perfect, but it was close. The closer you looked, the closer it got. It was as if the primes were obeying a kind of statistical law, a law that governed their average behavior, even if it could not predict their exact positions. Gauss had found a way to guess, with remarkable accuracy, how many primes there were in any given range. This was a profound moment in the history of mathematics. It was the first real evidence that the primes were not random, that there was a deep structure beneath their apparent chaos. But Gauss did not stop there. He did not just notice the pattern and move on. He spent years thinking about it, trying to understand why it was true. He never found a complete explanation. He never proved his guess, but he left it behind for others to work on, a gift to future generations of mathematicians. The pattern that Gauss noticed is now called the prime number theorem. It is one of the most important results in all of number theory, and it took more than 100 years to prove. The proof was completed independently by two mathematicians, Jacques Hadamard and Charles-Jean de la Vallée-Poussin, in the 1890s. They used tools that Gauss never had, tools that had been developed in the decades after his death. They showed that Gauss had been right, that his guess was not just a coincidence, but a genuine mathematical truth. But the prime number theorem, as important as it is, does not tell the whole story. It gives a rough approximation of how the primes are distributed. It does not give the exact distribution. It does not tell you where every prime is located. It gives you a map, but the map is blurry. The sharp edges, the exact details, are still missing. And that is where the Riemann hypothesis comes in. The Riemann hypothesis is not a separate problem from the prime number theorem. It is a refinement of it, a way of sharpening the blurry map into something perfectly clear. If the Riemann hypothesis is true, then mathematicians would have a complete understanding of the distribution of the primes. They would know exactly how many primes there are below any given number, and they would know the size of every gap between consecutive primes. They would have the precise map that Gauss had only been able to approximate. If the Riemann hypothesis is false, then the primes are more complicated than anyone has ever suspected. The blurriness would be real, not just a limitation of our current tools, but a feature of the universe itself. This is why the Riemann hypothesis is so important. It is not just a technical problem for specialists. It is the key to understanding one of the most basic and mysterious objects in all of mathematics. And it has remained unproven for more than 160 years. That is a long time. It is longer than anyone alive today has been alive. It is longer than the lifetimes of several generations of mathematicians. And yet, despite the efforts of some of the greatest minds in history, the hypothesis still stands, waiting for someone to either prove it or disprove it. There is a kind of quiet dignity in the way mathematicians have approached this problem. They have not given up. They have not stopped trying. They have built entire new branches of mathematics in the hope of solving it. They have checked billions of cases using computers, and every single one has supported the hypothesis. But they know that checking billions of cases is not a proof. They know that a proof requires something more, something that no computer can provide. A proof requires a chain of reasoning, a logical argument that shows, beyond any possible doubt, that the hypothesis must be true, and that chain of reasoning has never been found. The Riemann hypothesis is not the only unsolved problem about primes. There are others, some of which we have mentioned and some we have not. The Twin Prime Conjecture, the Goldbach Conjecture, the Mersenne prime problem, all of these are questions about the primes that have resisted solution for decades or centuries. They are all part of the same family of questions. Questions that ask how the primes are arranged, how they behave, what their limits are. And they are all still open. As you lie there in the dark, it is worth thinking about what it means for a problem to remain open for so long. It is not a sign of failure. It is not a sign that mathematicians are not clever enough. It is a sign that the problem is deep, that it touches on something fundamental about the nature of numbers. The primes are not just a puzzle to be solved. They are a window into the structure of the universe. They are a reminder that there is always more to learn, always more to understand, always more to discover. And that is not a bad thing. It is, in its own way, a kind of comfort. The world is full of mysteries. Some of them are small, like the mystery of where you left your keys. Some of them are large, like the mystery of why the universe exists at all. The primes are a mystery in between. They are not too large to think about, but they are large enough to remind you that there are things you do not know, things you may never know, and that is perfectly fine. The world does not require you to understand everything. It only requires you to be present, to be curious, to be willing to sit with the questions even when they do not have answers. So let the primes sit with you tonight. Let them be a quiet presence in the back of your mind. You do not need to solve them. You do not even need to understand them fully. You only need to know that they are there, that they are infinite, that they are mysterious, and that they will still be there tomorrow morning, waiting for anyone who wants to look at them. That is enough. That is more than enough. And as you drift further toward sleep, let the image of the primes settle into you. Picture them as stars in a vast sky, scattered across the darkness, some close together, some far apart, all of them moving to a rhythm that you can almost hear but cannot quite grasp. The stars have been there for a long time, and they will be there for a long time yet. You do not need to count them. You do not need to map them. You only need to look up every now and then and remember that they are there. That is what the primes are like. They are the stars of arithmetic, the lights in the mathematical sky, and they are still burning, still waiting, still infinite. Let your mind drift back now to the quiet streets of Alexandria, more than 2,000 years ago, where the first great library of the ancient world stood near the harbor, a place where scrolls were gathered from every corner of the known world, where scholars came to read and to think and to argue about the nature of things. It was in this city, in the centuries before the Common Era, that Euclid sat down with his scrolls and his stylus and began to organize everything that was known about shape and number into a single, coherent whole. He called it The Elements, and it would become one of the most influential books ever written, copied by hand for centuries, translated into every major language, studied in classrooms from Baghdad to Paris to London. It is still studied today, in its essentials, by children learning geometry for the first time. The shape of Euclid's reasoning, the way he built one idea on top of another, starting from axioms so simple that no one could deny them, and proceeding step by careful step to conclusions that no one could doubt, became the model for all of mathematics that followed. It is the pattern of thought that still underlies every proof, every theorem, every new piece of mathematical truth that has been added to the structure since. Buried in the middle of the elements, among the theorems about triangles and circles and the properties of lines, Euclid included a proof about prime numbers. It was not a practical proof. It did not help anyone measure land or build a temple or predict an eclipse. It was a proof for its own sake, a proof that something was true simply because it was true. Euclid wanted to know whether prime numbers ever ran out, whether there was a largest prime, a number so large that no larger one could be indivisible. He proved that there was no such number, that the primes are infinite, that no matter how far you go along the number line, there is always another prime waiting just beyond. His proof was simple, elegant, and final. It has never needed to be revised. It is as true today as it was the day he wrote it down. But Euclid's proof, as powerful as it was, left a question unanswered. The question was not whether primes are infinite. The question was how they are arranged. Euclid had shown that primes exist forever, but he had not shown where they are. He had not shown whether there was a pattern to their distribution, a rhythm to their appearance, a rule that could predict when the next one would arrive. This question, the question of arrangement, would remain unanswered for more than 2,000 years. It would become the central problem of number theory, the problem that Gauss and Riemann and so many others would devote their lives to understanding. It is the question that still sits at the heart of one of the most important unsolved problems in all of mathematics. As you lie there in the dark, it is worth thinking about what it means for a question to remain unanswered for so long. It is not as if no one has tried. Some of the greatest minds in history have turned their attention to the distribution of primes. They have built entire new branches of mathematics in the effort to understand it. They have checked billions of cases by hand and by computer, and still the question remains open. This is not a failure. It is a sign of how deep the question is. The primes are not just any numbers. They are the atoms of arithmetic, the fundamental building blocks from which every other number is made, and like atoms, they have a structure that is not immediately visible. You can see the building that is made from them, but the atoms themselves, the individual primes, are too small to see clearly. You have to look very closely, and even then, you only see glimpses. The question of how primes are distributed is the question of how these fundamental building blocks are arranged. It is the question of whether there is an order to the universe of numbers, or whether the universe of numbers is ultimately chaotic. Mathematicians have long suspected that there is an order, that the primes follow a deep and subtle pattern that is hidden from view. But they have not been able to prove it. The pattern is there, they believe, but it is written in a language they have not yet learned to read. The Riemann hypothesis is the key to that language. If it is true, the pattern becomes clear. If it is false, the pattern is more complicated than anyone has imagined. The Riemann hypothesis is not a simple problem. It is not something you can explain to a child in a few sentences, the way you can explain the Collatz Conjecture. It requires years of study just to understand what it is asking. But the idea behind it, the idea that the zeros of a certain function determine the distribution of primes, is something that can be felt even if it cannot be fully understood. It is the idea that there is a hidden order beneath the apparent chaos, a structure that is not visible on the surface, but that can be detected if you know where to look. This is a comforting idea, in its way. It suggests that the universe of numbers is not random, that there is a plan, a logic, a reason for the way things are. It suggests that even the most mysterious objects in mathematics are not beyond understanding, only beyond our current understanding. There is something else worth thinking about as you let this idea settle into you. The Riemann hypothesis is not just a problem for pure mathematicians. It has practical consequences. If the Riemann hypothesis is true, then mathematicians know a great deal about the distribution of primes, and that knowledge can be used to design more secure encryption systems, to improve the efficiency of certain algorithms, to solve problems in physics and engineering. If it is false, then the world is more complicated than we thought, and the encryption systems that rely on the difficulty of factoring large numbers may be more secure than we realized. Either way, the answer matters. It matters not just to mathematicians, but to everyone who uses a computer or a phone, everyone who sends a private message or makes a payment online. But the practical consequences are not the reason mathematicians want to solve the Riemann hypothesis. They want to solve it because it is there, because it is a mystery that has resisted all attempts to solve it, because it is a test of human ingenuity and perseverance. They want to solve it because they want to understand the primes, to see the pattern that has been hidden for so long. This is the deepest motivation in mathematics, the motivation that has driven people like Euclid and Gauss and Riemann to spend their lives thinking about numbers. It is not about practical results, it is about understanding. It is about seeing something clearly for the first time. And so the Riemann hypothesis sits there, at the center of number theory, a problem that has been worked on for more than a century and a half, a problem that has inspired entire fields of mathematics, a problem that remains, to this day, unsolved. It is the great unsolved mystery of the primes, the question that Euclid's proof left unanswered. And it is a reminder that even the simplest things, the things you learned in grade school, the numbers you use every day, can contain depths of mystery that no one has yet fully explored. The primes are simple, but they are not simple. They are ordinary, but they are not ordinary. They are the most basic objects in arithmetic, and they are the most mysterious. So let the Riemann hypothesis be a quiet presence in your mind tonight. You do not need to understand it fully. You do not need to solve it. You only need to know that it is there, that it is one of the great unanswered questions of mathematics, and that it has been there for a very long time. It will still be there tomorrow, and the day after, and for as long as anyone cares to think about it. It is a permanent feature of the mathematical landscape, a reminder that there is always more to know, always more to understand, always more to explore, and that is a comfort in its own way. The world is not simple, it is full of mysteries, and some of those mysteries are written in numbers. Let your attention drift now, away from the primes and their quiet, stubborn mysteries, and toward something that might feel even stranger, even more unsettling, because it touches not on what we know, but on the limits of knowing itself. There is a kind of knowledge that mathematics has always promised, a knowledge that feels absolute, certain, beyond any possible doubt. When Euclid proved that the primes are infinite, he did not offer a guess or a strong opinion. He offered a proof, a chain of reasoning so clear and so solid that it has never needed to be revised. That is the promise of mathematics, the promise that some things can be known with a certainty that nothing else in human life can match. And yet, in the early years of the 20th century, a discovery was made that would forever change what that promise meant. The story begins with a man named David Hilbert, a mathematician who was, in many ways, the embodiment of mathematical confidence. Hilbert believed that mathematics was the most reliable form of knowledge that humans had ever created. He believed that it was possible, in principle, to place all of mathematics on a single, unshakable foundation, a foundation so solid that no contradiction could ever arise within it, and from which every true mathematical statement could eventually be derived. This was not a modest ambition. It was a vision of mathematics as a complete, closed, and perfectly self-consistent system, a system that could answer any well-posed question that could ever be asked within it. Hilbert's program, as it came to be known, was the culmination of centuries of mathematical progress, the dream of a final, perfect foundation for all of human reasoning. But there was a problem, a crack in the foundation that had already begun to appear before Hilbert even formulated his program. A mathematician named Georg Cantor had been exploring the nature of infinity, and what he found was deeply unsettling. Cantor showed that infinity is not a single, simple concept. There are different sizes of infinity. The infinite collection of whole numbers, for example, is smaller than the infinite collection of all points along a continuous line. This was a shocking idea, and it provoked fierce resistance from some of Cantor's most respected contemporaries. They could not accept that there could be different kinds of infinity, that something as abstract and unbounded as infinity could be measured and compared. Cantor himself suffered greatly from this resistance, enduring years of professional isolation and personal distress. But his ideas were too powerful to be ignored. They forced mathematicians to confront the possibility that even the most basic concepts, like the idea of a collection of objects, might contain hidden complexities that had never been fully examined. The crack widened when a philosopher and mathematician named Bertrand Russell posed a question that seemed almost like a joke, but that revealed a genuine logical fault line running through the foundations of set theory. Russell asked about the collection of all collections that do not contain themselves as a member. If this collection contains itself, then by its own definition it shouldn't. If it doesn't contain itself, then by its own definition it should. Either answer leads to a contradiction. This is not a puzzle to be solved. It is a sign that something is wrong with the way mathematicians had been thinking about collections. The informal, intuitive approach that had worked for so long had hidden a deep flaw, and that flaw meant that the foundations of mathematics were not as solid as everyone had believed. These developments created an urgent need for a fresh start, a way to rebuild the foundations of mathematics from the ground up, using axioms so carefully chosen that no contradiction could ever arise. Hilbert's program was the most ambitious response to this need. He wanted to establish a finite set of axioms, a small number of starting points, from which every true mathematical statement could be proven, and from which no false statement could ever be derived. He wanted to give mathematics a foundation that was not only solid but also complete, a foundation that could answer every question that could be asked within its framework. This was a grand vision, and it seemed, for a time, within reach. But then, in 1931, a young Austrian logician named Kurt Gödel published a paper that changed everything. Gödel was in his 20s, relatively unknown, and his paper was dense and difficult. It took time for the mathematical community to fully understand what he had done. But when they did, they realized that he had shown something that no one had expected, something that would forever alter the way mathematicians thought about their own discipline. Gödel had proven that any mathematical system powerful enough to describe ordinary arithmetic would always contain statements that are true but cannot be proven within the system itself. This was not a limitation of human cleverness. It was a structural limitation of the system itself, a feature of the way that logic and proof are built. To understand what Gödel showed, it helps to think about the idea of self-reference. A statement that talks about itself can create strange loops that can lead to paradoxes or to truths that are beyond the reach of proof. Gödel constructed a mathematical sentence that essentially says, this sentence cannot be proven true. If the sentence is false, then it can be proven true, which would mean that a false statement has been proven, a contradiction. So the sentence must be true, but if it is true, then it cannot be proven true, because that is exactly what it says. The sentence is true, but it is unprovable. And because the sentence is built using the rules of the system itself, the system is incomplete. There is a truth that lies beyond its reach. Gödel's theorem is often called the incompleteness theorem, and it is one of the most important results in the history of logic. It shows that no single, fixed set of axioms can capture all of mathematical truth. There will always be truths that are beyond the reach of any given system. You can expand the system, add new axioms, and capture some of those truths. But the new system will then have its own unprovable truths. The process can go on forever, and it will never reach an end. Truth is bigger than proof. There is no final, complete, self-certifying foundation for mathematics. Hilbert's dream, the dream of a complete and closed mathematical system, was not just difficult to achieve. It was impossible in principle. This is a strange and humbling idea, and it takes time to settle in. It is not that there are truths that we have not yet found. It is that there are truths that cannot be found, not by any fixed method, not by any finite set of rules. They are there, waiting, but they are beyond the reach of proof. Gödel's theorem does not tell us which statements are unprovable. It only tells us that such statements must exist. And it raises a question that has haunted mathematicians ever since. Are the great unsolved problems, the Riemann Hypothesis, the Twin Prime Conjecture, the P versus NP question, simply difficult, waiting for a clever enough proof, or are they unprovable, truths that sit beyond the reach of any fixed system of axioms? No one knows. There is no way to know in advance. The uncertainty is built into the structure of mathematics itself. As you lie there in the dark, let this thought rest with you. Mathematics, the most certain form of knowledge humans have ever created, contains its own limit. It cannot prove everything. It cannot certify itself. It is a tool that works beautifully, that has built bridges and flown airplanes and put humans on the moon, but it is not a tool that can ever be fully complete. There will always be more to know, more to explore, more to understand. And that is not a failure. It is a feature of the landscape. It is what makes mathematics endlessly interesting. It is what keeps mathematicians working, generation after generation, on problems that may never be fully resolved. Gödel's theorem was not the end of the story. A few years later, a British mathematician named Alan Turing was thinking about a related question, one that would connect Gödel's abstract logic to the emerging world of computers. Turing asked whether it was possible to build a machine that could determine, in advance, whether any given computer program would eventually finish running or would run forever without stopping. He proved that no such machine could exist. There will always be programs whose behavior cannot be predicted by any fixed set of rules. This became known as the halting problem, and it is essentially the same idea as Gödel's incompleteness theorem, expressed in the language of computation rather than logic. The limits of proof are the limits of computation. There are questions that cannot be answered by any machine, no matter how powerful, no matter how cleverly designed. Turing's proof is important for another reason too. It shows that the limits of mathematics are not abstract or theoretical. They are practical. They affect the machines that run our world, the algorithms that secure our data, the programs that control our infrastructure. There are questions that no computer can ever answer, not because computers are not powerful enough, but because the answers are not computable in principle. This is a sobering thought, but it is also a reminder that the world is not simple. It is full of complexity, full of mysteries, full of things that resist easy explanation. But the story does not end with Turing either. There is another layer, another set of questions that grew out of Gödel's and Turing's work. If some truths are unprovable and some problems are uncomputable, then what about the rest? What about the problems that are computable, that can be solved by machines, but that take an impossibly long time to solve? This is the question of computational complexity, the question of how hard it is to solve a problem, and it leads to one of the most important unsolved problems in all of mathematics, the P versus NP problem. The P versus NP problem is, in a sense, the practical cousin of Gödel's incompleteness theorem. It asks whether problems that are easy to check are also easy to solve. You have already encountered this idea in the earlier sections of tonight's journey, in the image of the jigsaw puzzle and the combination lock. But it is worth returning to it here, in the context of Gödel and Turing, because it shows that the limits of knowledge are not just about what can and cannot be proven, they are also about what can and cannot be computed in a reasonable amount of time. The class of problems that can be solved quickly is called P. The class of problems that can be checked quickly is called NP. Every problem in P is also in NP, because if you can solve something quickly, you can certainly check a proposed answer quickly too. The question is whether the reverse is true. Is every problem that is easy to check also secretly easy to solve, given a clever enough method that nobody has thought of yet? The evidence suggests that the answer is no, that there are problems that are fundamentally harder to solve than to check. But no one has been able to prove it. The question has been open for more than 50 years, and it has resisted every attempt at a solution. The P versus NP problem is important for many reasons. It has practical consequences for cryptography, for logistics, for artificial intelligence, and for countless other fields. But it is also important for a deeper reason. It is a question about the nature of difficulty itself. It asks whether there is a fundamental difference between finding a solution and verifying a solution, whether the universe of computational problems is divided into two distinct categories, the ones that are easy and the ones that are hard. And it asks this question in a way that echoes the questions that Gödel and Turing were asking. If some truths are unprovable and some problems are uncomputable, then what about the ones in between? Are they all equally easy, or are they divided into degrees of difficulty that reflect some deeper structure of the mathematical landscape? As you lie there, letting these ideas wash over you, it is worth thinking about what it means for a problem to remain open for so long. The Riemann hypothesis has been open for more than 160 years. The P versus NP problem has been open for more than 50 years. These are not problems that people have stopped working on. They are problems that people have devoted their entire careers to, problems that have inspired entire fields of mathematics and computer science, and they are still open. That is not a sign of failure. It is a sign of how deep the questions are. It is a sign that there is still something fundamental that we do not understand, something hidden beneath the surface of the ordinary, something that will take time and patience and insight to uncover. There is a kind of peace in this, if you let yourself feel it. The world is not simple. It is full of mysteries, full of questions that do not have easy answers. And that is okay. It is okay to not know. It is okay to sit with the questions, to let them rest in the back of your mind, to let them come and go without needing to resolve them. The questions will still be there tomorrow. They will still be there next year. They will still be there for as long as anyone cares to think about them. And in the meantime, the world will continue to work. The phone will continue to protect your messages. The airplanes will continue to fly. The blood will continue to move through your veins, all on top of a foundation of mathematics that is only partially understood. That is the quiet comfort of tonight. The uncertainty is not a threat. It is a reminder that there is always more to learn, always more to explore, always more to understand. And that is enough. That is more than enough. You do not need to solve the problems. You do not need to understand them fully. You only need to know that they are there, that they have been there for a long time, and that they will be there for a long time yet. They are part of the landscape, part of the world, part of the quiet, ongoing work of human understanding. And that work will continue, whether you are awake or asleep, whether you are paying attention or drifting. It will continue, quietly, patiently, one step at a time. Let your mind settle now into a quieter space, a place where the numbers and proofs and theorems drift a little further away, and where something more physical, more tangible, begins to take shape. You have been thinking about primes and infinities and the limits of proof. But there is another kind of unsolved problem, one that does not live in the abstract world of pure mathematics, but in the actual, physical world of water and air, of smoke and storms, of the blood moving through your own body at this very moment. This is the problem of fluid motion, the problem of understanding how liquids and gases flow, how they swirl and twist and sometimes settle into patterns so complex that even the most powerful computers in the world cannot fully predict them. The story of this problem begins with two men, Navier in France and Stokes in Britain, working in the early part of the 19th century. They were both interested in the physics of fluids, in the way that water moves through a pipe, the way that air moves around a solid object, the way that currents form and dissipate in the ocean. They developed a set of equations that describe this motion mathematically, taking into account the speed of the fluid, its pressure, its thickness, and the friction that slows it down. These equations, which now bear their names, the Navier-Stokes equations, are among the most important and most useful equations in all of applied mathematics. Engineers use them every day to design airplanes, to predict the weather, to model the flow of blood through arteries, to understand the movement of ocean currents. The equations work. They have been tested again and again, in countless experiments and real-world applications, and they have always produced results that match the observed behavior of fluids with extraordinary accuracy. And yet, for all their practical success, there is a gap at the heart of the Navier-Stokes equations, a gap that has never been closed. The gap is this: mathematicians have not been able to prove that the equations always behave sensibly. They have not been able to prove that, starting from any reasonable initial condition, the equations will always produce a smooth, well-behaved solution that continues forever into the future, without ever breaking down into something that makes no mathematical sense. It is possible, as far as anyone has been able to determine, that there exists some starting condition, some particular configuration of fluid motion that causes the equations to produce an infinity in a finite amount of time, a point where the speed or the pressure becomes infinite, where the mathematics simply stops working. No one has ever found such a configuration, but no one has ever proven that such a configuration cannot exist. To understand why this matters, it helps to think about what the Navier-Stokes equations are actually doing. They are describing the motion of a fluid, a continuous substance that fills space and moves according to certain rules. If you pour a cup of water, the water does not behave randomly. It follows a pattern that is governed by the laws of physics. The Navier-Stokes equations are an attempt to capture that pattern in mathematical form. They are an attempt to say, given the state of the fluid at one moment, what will its state be at the next moment, and the moment after that, and the moment after that. This is a powerful idea, the idea that you can predict the future of a physical system by applying a set of mathematical rules. But the power of the idea depends on the reliability of the rules. If the rules themselves can break down, if they can produce an answer that is not physically meaningful, then the predictive power is limited. The Navier-Stokes equations are not the only equations that have this kind of problem. There are other equations in physics that are also difficult to analyze, that also have gaps in our understanding. But the Navier-Stokes equations are special because they are so widely used, and because the gap in our understanding is so fundamental. It is not a gap about some obscure detail. It is a gap about whether the equations are even mathematically consistent in the first place. It is a gap that has been open for more than a century and a half, and it is one of the 7 Millennium Prize problems, with $1 million reward for anyone who can close it. As you lie there letting this thought settle, it is worth thinking about what it means for a set of equations to be both extraordinarily useful and yet not fully understood. It is a strange situation, and it is not unique to the Navier-Stokes equations. It happens in many areas of mathematics and physics, where the practical success of a theory far outstrips the theoretical understanding of why it works. Engineers build bridges using equations that are only partially proven. Doctors use medical imaging techniques that rely on mathematical ideas that are still being explored. The world works, and it works well, on top of a foundation that is not fully secure. This is not a failure. It is a reminder that the world is complex, and that human understanding is always incomplete. There is a related phenomenon that makes the Navier-Stokes equations even more difficult to study, and it is a phenomenon that you have probably experienced without even realizing it. It is the phenomenon of turbulence. When a fluid moves slowly and smoothly, it follows a predictable pattern. The flow is orderly, layered, easy to describe. This is called laminar flow. But when a fluid moves faster, or when it encounters an obstacle, the flow can become chaotic, swirling, unpredictable. This is turbulence. Turbulence is everywhere, in the smoke rising from a candle, in the water rushing over rocks in a stream, in the air buffeting an airplane as it descends through a storm. It is one of the most common and most complicated phenomena in the physical world, and it is one of the least understood. The Navier-Stokes equations are the equations that would, in principle, describe turbulence. They are the equations that would tell you exactly how the swirls form, how they grow, how they interact, how they eventually dissipate. But turbulence is so complex that even with the equations, even with the most powerful computers, it is almost impossible to predict in detail. The equations are there, but they are too difficult to solve. The mathematics is too hard. The phenomenon is too rich and too subtle. And so, even though the equations are known, the behavior they describe remains largely a mystery. There is a story from the 1960s that captures this difficulty beautifully. A meteorologist named Edward Lorenz was running a computer simulation of weather patterns using a simplified set of equations that were related to the Navier-Stokes equations. He was trying to predict the weather, and he was doing a good job of it. But one day, he ran a simulation, and then he ran it again with a slightly different starting value. The difference was tiny, so small that he thought it would not matter, but it did matter. The two simulations diverged almost immediately, producing completely different weather patterns after only a short simulated time. Lorenz had stumbled upon what is now called the butterfly effect, the idea that small changes in initial conditions can lead to large changes in outcomes. This is a fundamental property of turbulent systems, and it means that even if you had perfect equations, you would never be able to predict the weather more than a few days in advance, because you would never be able to measure the initial conditions with enough precision. The uncertainty would grow too quickly. The butterfly effect is not a failure of the Navier-Stokes equations. It is a feature of the systems they describe. It is a reminder that some things are inherently unpredictable, not because we do not know the rules, but because the rules themselves lead to chaotic behavior. This is a humbling idea, but it is also a beautiful one. It means that the world is not simple, that it is full of complexity and richness, that there is always more to understand, always more to explore. The Navier-Stokes equations are a window into that complexity, a window that is partly clear and partly fogged. They show us something true about the world, but they also show us how much we do not know. So let the Navier-Stokes equations sit with you tonight, not as a problem to be solved, but as a reminder of the mystery that lies beneath the surface of the ordinary. The water in a glass, the air in a room, the blood in your veins, all of it is moving according to rules that are only partially understood. And yet it moves anyway, reliably, predictably, without needing a proof to keep going. There is a kind of peace in that, a kind of trust that the world will continue to work even if we do not fully understand it. That is the gift of the Navier-Stokes equations, the gift of uncertainty, the gift of mystery, the gift of knowing that there is always more to learn and that the learning itself is a kind of rest. Let your mind drift now from the swirling currents of fluids and turbulence towards something more still, more geometric, more rooted in the ancient soil of mathematics. There is a branch of mathematics that deals with shapes, but not the shapes you can hold in your hand or see with your eyes. These are shapes that live in the abstract world of equations, shapes that are defined not by physical boundaries but by mathematical relationships. This is the world of algebraic geometry, and it is one of the deepest and most beautiful areas of modern mathematics. It is also the home of several unsolved problems that have resisted every attempt at a solution for decades, problems that sit at the very edge of what mathematicians currently understand. The story of this world begins with equations, the kind of equations you might have seen in school, where you have variables and constants, and you try to find the values that make the equation true. But in algebraic geometry, the equations are not just problems to be solved, they are descriptions of shapes. A simple equation like x squared plus y squared equals 1 describes a circle. A more complicated equation can describe a curve, a surface, or even a shape that exists in dimensions far beyond the three you are familiar with. These shapes, defined by polynomial equations, are the objects of study in algebraic geometry. They are the landscapes that mathematicians explore, and they are full of mysteries. One of the most important kinds of shapes in algebraic geometry is called an elliptic curve. Despite the name, an elliptic curve has nothing to do with an ellipse. It is a particular kind of curve defined by a specific type of equation, one that looks like y squared equals x cubed plus ax plus b, where a and b are constants. Elliptic curves are fascinating objects. They are simple enough to be studied with relatively basic tools, yet they are rich enough to contain deep mathematical secrets. They show up in number theory, in cryptography, and in the proof of Fermat's last theorem, which we mentioned earlier tonight. They are everywhere in modern mathematics, and they are still not fully understood. The mystery that surrounds elliptic curves is tied to a question about their points. A point on an elliptic curve is simply a pair of numbers, x and y, that satisfy the equation. But mathematicians are not interested in just any points. They are interested in points whose coordinates are rational numbers, numbers that can be written as fractions. These are called rational points. Sometimes an elliptic curve has only a finite number of rational points. Sometimes it has infinitely many. The question of which curves have finitely many rational points and which have infinitely many is one of the deepest questions in number theory, and it is the subject of a conjecture known as the Birch and Swinnerton-Dyer Conjecture. The Birch and Swinnerton-Dyer Conjecture, first proposed in the 1960s by two British mathematicians, Brian Birch and Peter Swinnerton-Dyer, offers a way to predict, in advance, whether a given elliptic curve has finitely many or infinitely many rational points. The prediction is based on the behavior of a related mathematical function, a function that is similar in spirit to the zeta function that Riemann used to study the primes. The conjecture says that if this related function has a certain property, then the curve has infinitely many rational points. If it has a different property, then the curve has only finitely many. This is a powerful idea, a way of reading the properties of a curve from the behavior of a function that is associated with it. To make this more concrete, imagine that each elliptic curve has a kind of fingerprint, a unique signature that tells you something about its structure. The Birch and Swinnerton-Dyer conjecture says that you can read this fingerprint to determine whether the curve contains an infinite number of rational points. It is a bit like being able to tell whether a forest contains an infinite number of trees just by listening to the sound of the wind. The sound is related to the forest, but the connection is not obvious. The conjecture provides the connection, but it has never been proven. What makes the Birch and Swinnerton-Dyer conjecture especially interesting is how it was discovered. Birch and Swinnerton-Dyer were among the first mathematicians to use a computer for pure mathematical research. In the early 1960s, they had access to a machine called EDSAC, one of the first electronic computers. They used it to calculate data about many different elliptic curves, running what were essentially experiments. They looked at the data and noticed a pattern. The pattern was not obvious. It emerged only after they had looked at many curves and many calculations. But once they saw it, they knew they had found something important. The conjecture they proposed was a direct result of this computer-assisted pattern recognition, a reminder that computers can be more than just calculators. They can be tools for discovery. The Birch and Swinnerton-Dyer conjecture has been confirmed for many specific elliptic curves. Mathematicians have checked it in thousands of cases, and it has always held up. But a confirmation of many cases is not a proof. A proof would require a general argument, one that covers every possible elliptic curve, no matter how strange or unusual. That proof has never been found. It remains one of the most important open problems in mathematics, one of the 7 Millennium Prize problems, with a $1 million reward for anyone who can solve it. There is a reason why the Birch and Swinnerton-Dyer conjecture is so difficult to prove. It connects two different areas of mathematics, number theory and complex analysis, in a deep and unexpected way. The related function that the conjecture relies on is a complex function, one that is defined on the complex numbers, the same kind of two-part numbers that Riemann used in his study of the zeta function. This function is a kind of bridge between the abstract world of elliptic curves and the analytic world of functions and limits. The conjecture says that the behavior of this bridge determines the rational points on the curve. It is a deep connection, and it is not yet fully understood. The story of elliptic curves and the Birch and Swinnerton-Dyer conjecture is closely tied to another story, one that we mentioned earlier tonight, the story of Fermat's last theorem. Fermat's last theorem was the famous margin note from the 17th century, the claim that no three positive whole numbers could satisfy an equation of the form x to the n plus y to the n equals z to the n, when n is greater than 2. It took 350 years to prove, and the proof, when it finally came, was built on the theory of elliptic curves. The proof was the work of Andrew Wiles, a mathematician who had been fascinated by Fermat's theorem since childhood. Wiles worked on the problem in secret for 7 years, telling almost no one what he was doing. He knew that if he could prove a particular conjecture about elliptic curves, called the modularity conjecture, then Fermat's theorem would follow as a consequence. The modularity conjecture said that every elliptic curve with rational coefficients was secretly a modular form, a completely different kind of mathematical object. Wiles spent years trying to prove this conjecture for a specific family of elliptic curves, the ones that were relevant to Fermat's theorem. In 1993, he announced that he had done it. The announcement was met with excitement and celebration, but then a gap was found in the proof, a specific technical step that did not quite work. Wiles spent another year working on the gap, with the help of a former student, Richard Taylor. They eventually found a way around it, and the corrected proof was published in 1995. The 350-year-old problem was finally solved. The proof of Fermat's last theorem is a reminder that even the most difficult problems can be solved, and that the solutions often come from unexpected directions. The theory of elliptic curves, which had been developed for its own sake, turned out to be exactly the tool needed to solve a problem that had seemed unrelated. This is a pattern that appears again and again in mathematics. Ideas that are developed for one purpose often turn out to be useful for another. The connections between different areas of mathematics are deep and often hidden. The Birch and Swinnerton-Dyer conjecture is another example of this pattern. It connects elliptic curves to complex analysis, and it remains one of the most important unsolved problems in all of mathematics. As you lie there, letting these ideas settle, it is worth thinking about what it means for a problem to remain unsolved for so long. The Birch and Swinnerton-Dyer conjecture has been open for more than 60 years. That is a long time. It is longer than the careers of many mathematicians. It is long enough that the people who first proposed it are no longer working on it, and the people working on it now were not even born when it was proposed. The problem has been passed down through generations of mathematicians, each one adding a small piece to the puzzle, each one hoping that the next piece will be the one that completes the picture. But the picture is still incomplete. The conjecture is still unproven. This is not a failure. It is a sign of how deep the problem is. The Birch and Swinnerton-Dyer conjecture is not a simple problem. It is a problem that touches on some of the most fundamental questions in mathematics, questions about the nature of numbers, about the structure of equations, about the connections between different areas of mathematics. It is a problem that requires a deep understanding of many different fields, and a problem that has resisted every attempt at a solution. It is a reminder that the world of mathematics is not a simple world. It is a world full of complexity and mystery, a world where even the most elegant and beautiful ideas can be difficult to prove. And yet, despite the difficulty, mathematicians continue to work on the Birch and Swinnerton-Dyer conjecture. They continue to look for new approaches, new tools, new ways of thinking about the problem. They do this not because they expect an easy solution, but because they believe the problem is worth solving. They believe that understanding the rational points on elliptic curves will deepen our understanding of numbers themselves. They believe that the connections between elliptic curves and complex analysis are part of a deeper structure that has not yet been fully explored. And they believe that the problem, difficult as it is not beyond reach. So let the Birch and Swinnerton-Dyer conjecture be a quiet presence in your mind tonight. It is a problem about curves and points and rational numbers. It is a problem about the deep structure of mathematics. It is a problem that has been open for more than 60 years, and it will still be open tomorrow. There is no need to solve it. There is no need to understand it fully. You only need to know that it is there, that it is one of the great unsolved problems of mathematics, and that it is a reminder that the world of numbers is full of mystery and beauty. That is enough. That is more than enough. Let your attention drift now from the curves and equations of algebraic geometry towards something stranger, something that connects the world of shapes you can see with the world of shapes you can only imagine. There is a branch of mathematics called topology, and it is concerned with the properties of shapes that survive stretching, bending, and twisting, but not tearing or gluing. To a topologist, a coffee mug and a donut are the same shape because you can deform one into the other without cutting or tearing it. The mug's handle becomes the donut's hole, and the body of the mug becomes the donut's body. This is a different way of thinking about shapes, a way that ignores the details of size and angle, and focuses instead on the underlying structure, the connections, the holes, the ways that different parts of the shape are linked together. Topology is a deep and beautiful subject, and it has given rise to one of the most famous unsolved problems in all of mathematics, a problem that connects topology to another branch of mathematics called algebraic geometry. This problem is called the Hodge Conjecture, and it was first proposed by a Scottish mathematician named William Hodge in the 1950s. The Hodge Conjecture is a question about the relationship between two different ways of understanding shapes. One way comes from topology, the flexible, bendable world where shapes can be deformed at will. The other way comes from algebraic geometry, the rigid, precise world where shapes are defined by equations. The Hodge conjecture asks whether certain shapes that arise naturally in the topological world can always be built out of pieces that come from the algebraic world. To understand why this is a difficult question, it helps to think about what shapes look like in higher dimensions. You are familiar with shapes in 2 dimensions and 3 dimensions. A circle is a 2-dimensional shape, a sphere is a 3-dimensional shape. But in topology and algebraic geometry, shapes can exist in 4 dimensions, 5 dimensions, 6 dimensions, or even higher. These higher dimensional shapes cannot be pictured in the ordinary sense. You cannot draw a 4-dimensional sphere or hold a 5-dimensional donut in your hand. But mathematicians can still study these shapes, using equations and logical reasoning, because the rules of mathematics do not depend on the number of dimensions. The equations work the same way in any dimension, and the logical arguments are just as valid. The Hodge conjecture is about a particular kind of higher dimensional shape, one that arises from the study of a technique called harmonic analysis. Harmonic analysis is a way of breaking complicated things down into simpler pieces. You might have encountered this idea in music. A complex sound, like a chord played on a piano, can be broken down into a combination of simpler sounds, the individual notes that make up the chord. In the same way, A complicated shape can be broken down into simpler pieces, pieces that are easier to understand. The Hodge conjecture says that for certain well-behaved shapes, the pieces that come from this decomposition can always be traced back to algebraic geometry. They can always be built out of the rigid, equation-defined shapes that are the objects of study in algebraic geometry. This is a subtle and technical statement, and it is not easy to explain in plain language, but the underlying idea is simple. The Hodge conjecture is asking whether two different ways of understanding shapes are ultimately the same. It is asking whether the flexible world of topology and the rigid world of algebraic geometry are connected in a deep and fundamental way. Mathematicians have proven that this is true in many specific cases. They have shown that for certain kinds of shapes, the topological pieces can indeed be built out of algebraic pieces, but they have not been able to prove it in general. The conjecture remains open, one of the 7 Millennium Prize problems, with $1 million reward for anyone who can solve it. The Hodge conjecture is a problem that sits at the intersection of two of the most important branches of modern mathematics. It is a problem that requires a deep understanding of both topology and algebraic geometry, and it is a problem that has resisted every attempt at a solution for more than 70 years. It is a reminder that the connections between different areas of mathematics are not always obvious, and that the deepest truths often lie at the boundaries between disciplines. It is also a reminder that there are still many things we do not understand about the shapes that live in higher dimensions, the shapes that cannot be seen, but that can be studied with equations and logic. As you lie there, letting these ideas settle, it is worth thinking about what it means for a problem to be both simple to state and difficult to solve. The Hodge conjecture can be stated in a few sentences, but its solution would require a deep understanding of some of the most advanced mathematics that exists. It is a problem that is accessible to only a small number of people in the world, and it is a problem that may take many more years to solve. This is not a failure. It is a sign of how deep the problem is. The Hodge conjecture touches on some of the most fundamental questions in mathematics. Questions about the nature of shapes, about the connections between different areas of mathematics, about the structure of the mathematical universe itself. It is a problem worth thinking about, even if you cannot solve it, because it reminds you that there is always more to learn, always more to understand, always more to explore. The Hodge conjecture is closely connected to the work of a French mathematician named Alexander Grothendieck, one of the most influential and unusual figures in 20th century mathematics. Grothendieck rebuilt large portions of algebraic geometry from the ground up, developing an extraordinarily abstract and general framework that gave mathematicians powerful new tools for understanding shapes. He was known for his obsession with generality, his belief that the broadest possible version of a problem was often the easiest to solve. He worked in relative isolation for much of his career, and later in life he withdrew from mathematics entirely, moving to a remote village in the Pyrenees Mountains. His work remains a foundation for much of modern algebraic geometry, and it is still being studied and extended by mathematicians around the world. The Hodge conjecture is also connected to the work of William Hodge himself, who developed the theory of harmonic analysis for shapes. Hodge was a Scottish mathematician who spent much of his career at Cambridge University. He was interested in the relationship between topology and algebraic geometry, and he developed a powerful set of tools for studying this relationship. His conjecture was a natural extension of his work, a way of asking whether the tools he had developed were powerful enough to capture the full structure of the shapes he was studying. The conjecture has inspired generations of mathematicians, and it remains one of the most important open problems in the field. So let the Hodge conjecture be a quiet presence in your mind tonight. It is a problem about shapes and dimensions and the connections between different areas of mathematics. It is a problem that has been open for more than 70 years, and it will still be open tomorrow. There is no need to solve it. There is no need to understand it fully. You only need to know that it is there, that it is one of the great unsolved problems of mathematics, and that it is a reminder that the mathematical universe is full of mystery and beauty. That is enough. that is more than enough. Let your attention drift now from the abstract shapes and higher dimensions towards something far more concrete, far more physical, something that is happening inside your own body at this very moment. The atoms that make up your bones, your blood, your breath, they are all held together by forces that are described by a branch of physics called quantum field theory. And at the heart of quantum field theory is a mathematical framework that has been tested more precisely than almost any other theory in the history of science. It is called Yang-Mills theory, and it is one of the most successful and most important ideas in modern physics. It describes the forces that hold atomic nuclei together, the forces that govern the behavior of the fundamental particles that make up everything you can see and touch. It has been confirmed by experiments in particle accelerators, by decades of careful measurement, by the accumulated weight of millions of observations. And yet, for all its success, there is a gap in our understanding of Yang-Mills theory, a gap that forms one of the 7 Millennium Prize problems. The gap is called the Yang-Mills existence and mass gap problem. It is a question about whether the equations of Yang-Mills theory always produce solutions that make sense, and whether those solutions always have a particular property that physicists have observed in experiments. The property is called the mass gap, and it refers to the fact that the particles described by Yang-Mills theory, particles called gluons, never appear with zero mass. They always have at least some minimum amount of mass, a smallest possible value that is greater than zero. This is not something that physicists have assumed. It is something they have observed over and over again in experiments that are among the most precise ever performed. But they have not been able to prove it. They have not been able to show, from the equations themselves, that the mass gap must exist. They have not been able to show that the equations always behave sensibly, that they never produce a solution that breaks down into nonsense. To understand why this matters, it helps to think about what Yang-Mills theory actually describes. The theory was developed in the 1950s by 2 physicists, Chen-Ning Yang and Robert Mills. They were trying to solve a specific problem about the behavior of particles, and they developed a mathematical framework that turned out to be far more general and far more powerful than they had anticipated. Their theory describes the strong force, the force that holds protons and neutrons together inside atomic nuclei. This force is responsible for the existence of stable matter. Without it, the positively charged protons in a nucleus would repel each other and fly apart. The strong force is what keeps them together, and it is described by Yang-Mills theory. The particles that carry the strong force are called gluons, and they are named for their role in gluing the components of the nucleus together. Gluons are strange particles. They do not behave like the particles you might be familiar with, like electrons or photons. They are confined to the interior of atomic nuclei, and they never appear as free particles. They always exist in bound states, combined with other particles to form the protons and neutrons that make up ordinary matter. This confinement is a consequence of the mass gap. The gluons have a minimum mass, and that minimum mass limits the range of the strong force. It keeps the force confined to the tiny distances of the atomic nucleus, and it prevents it from reaching out to influence the wider world. The mass gap is a fundamental feature of the physical universe. It is the reason that matter is stable, the reason that atoms can exist, the reason that you are here, lying in this room, listening to this voice. And yet, despite its fundamental importance, it has never been proven mathematically. Physicists have observed it in experiments, and they have developed approximate methods that reproduce it with extraordinary accuracy, but they have not been able to prove it from first principles. They have not been able to show that the equations of Yang-Mills theory necessarily imply the existence of a mass gap. This is not because physicists are not clever enough. It is because the problem is genuinely difficult. It requires a deep understanding of quantum field theory, a subject that is itself one of the most complex and subtle areas of modern physics. The Yang-Mills existence and mass gap problem is closely related to another problem that we have discussed tonight, the Navier-Stokes existence and smoothness problem. Both problems are about the behavior of equations that describe physical systems. Both problems ask whether the equations always produce sensible solutions. Both problems have resisted solution for decades. But there is a difference. The Navier-Stokes equations describe a classical system, a system that behaves according to the rules of classical physics. The Yang-Mills equations describe a quantum system, a system that behaves according to the rules of quantum mechanics. Quantum systems are inherently more difficult to understand. They are governed by probabilities and uncertainties, and they involve particles that cannot be observed directly. The Yang-Mills problem is harder than the Navier-Stokes problem, and it has been open for just as long. As you lie there, letting these ideas settle, it is worth thinking about what it means for a physical theory to be both extraordinarily successful and yet not fully understood. Yang-Mills theory is one of the most precisely tested theories in the history of science. It has been confirmed by experiments that measure quantities to a precision of 1 part in a billion. It is the foundation of the Standard Model of particle physics, a theory that describes all of the known fundamental particles and their interactions. And yet, there is a gap in our understanding. The theory works, but we do not fully know why. The mass gap is there, but we cannot prove it. This is not a failure. It is a sign of how deep the theory is, how much it contains, how much there is still to learn. There is a parallel here with the other Millennium Prize problems we have discussed. The Riemann Hypothesis is about the distribution of primes, and it has been open for more than 160 years. The Navier-Stokes problem is about the behavior of fluids, and it has been open for more than a century. The P versus NP problem is about the nature of computation, and it has been open for more than 50 years. The Yang-Mills problem is about the nature of quantum fields, and it has been open for more than 60 years. All of these problems are deep. All of them have resisted every attempt at a solution. All of them are signs of the limits of our current understanding. The Yang-Mills problem is also connected to a deeper question, a question about the relationship between mathematics and physics. The equations of Yang-Mills theory are mathematical objects, and they can be studied independently of their physical meaning. They are objects of pure mathematics, objects that can be analyzed and understood without reference to the physical world. But they are also physical objects, objects that describe the behavior of real particles. The Yang-Mills problem asks whether the mathematical structure of the equations implies the physical phenomenon of the mass gap. It asks whether the mathematics and the physics are in harmony, whether the equations that describe the world are also consistent with the world they describe. This is a question that goes to the heart of the relationship between mathematics and physics, and it is a question that has not yet been answered. So let the Yang-Mills problem be a quiet presence in your mind tonight. It is a problem about particles and forces and the nature of matter. It is a problem about the deep structure of the physical universe. It is a problem that has been open for more than 60 years, and it will still be open tomorrow. There is no need to solve it. There is no need to understand it fully. You only need to know that it is there, that it is one of the great unsolved problems of mathematics and physics, and that it is a reminder that even the most successful theories can contain mysteries. That is enough. That is more than enough. Let your mind drift now from the quantum world of particles and fields towards something that feels almost like a puzzle, a riddle you could share with a child. There is a problem in mathematics that is so simple to state that you could explain it to anyone in less than a minute. It involves nothing more than a rule that tells you what to do with a number, and then another number, and then another, over and over again. It is a rule so simple that you could follow it with a pencil and a piece of paper, without any special training, without any knowledge of advanced mathematics. And yet, despite its simplicity, this problem has resisted every attempt at a solution for nearly 90 years. It is called the Collatz Conjecture, and it is one of the most frustrating and most beautiful unsolved problems in all of mathematics. The rule is this: take any whole number you like. If it is even, divide it by 2. If it is odd, multiply it by 3 and then add 1. Now take whatever number you land on, and do exactly the same thing again. Follow the rule over and over, indefinitely. The Collatz conjecture claims that no matter which whole number you start with, this process will always, eventually, lead you to the number 1. Once you reach 1, the pattern becomes a loop. 1 is odd, so you multiply by 3 and add 1, which gives you 4. 4 is even, so you divide by 2, which gives you 2. 2 is even, so you divide by 2 again, which gives you 1. And then you are back where you started. The conjecture says that every starting number eventually falls into this loop, that no matter how far you go, no matter how large the numbers become along the way, you will always, eventually, reach 1. Try it yourself, quietly, with a small number. Start with 6. 6 is even, so you divide by 2, landing on 3. 3 is odd, so you multiply by 3 and add 1, landing on 10. 10 is even, so you divide by 2, landing on 5. 5 is odd, so you multiply by 3 and add 1, landing on 16. 16 divides down cleanly. 8, 4, 2, 1. It works. Start with 7. 7 is odd, so you multiply by 3 and add 1, landing on 22. 22 is even, so you divide by 2, landing on 11. 11 is odd, so you multiply by 3 and add 1, landing on 34. 34 is even, so you divide by 2, landing on 17. 17 is odd, so you multiply by 3 and add 1, landing on 52. 52 is even, so you divide by 2, landing on 26. 26 is even, so you divide by 2, landing on 13. 13 is odd, so you multiply by 3 and add 1, landing on 40. 40 is even, so you divide by 2, landing on 20. 20 is even, so you divide by 2, landing on 10. And from 10 you already know the path, down to 5, to 16, to 8, to 4, to 2, to 1. It works again. Mathematicians have checked this conjecture for every single whole number up into the hundreds of trillions, and it has held true every single time. They have used powerful computers to run this simple rule for starting numbers that are so large they cannot even be written down in ordinary digits, numbers with thousands of digits, and every single one of them eventually reaches 1. The evidence is overwhelming, and yet no one has been able to prove it. No one has been able to show, with the kind of rigorous logic that mathematics demands, that this process must always end at 1 for every possible starting number, no matter how large. It remains possible, as far as anyone has proven, that somewhere out there, far beyond the range of numbers that have been checked, there exists some strange starting number that either climbs upward forever, never coming back down, or that falls into a different loop, a cycle that never reaches 1. No one has ever found such a number. No one has ever proven that 1 cannot exist. The Collatz conjecture is often described as a problem that is simple to state but almost impossible to solve. It is a problem that has attracted the attention of some of the greatest mathematicians in history, and it has frustrated every one of them. There is something about the problem that resists the usual tools of mathematics. It does not seem to fit neatly into any of the established branches of the subject. It is not quite number theory, not quite analysis, not quite combinatorics. It sits in a strange, isolated corner of mathematics, and it refuses to yield to any of the standard methods. There is a reason why the Collatz conjecture is so difficult. The process it describes is deeply unpredictable. When you start with a number, you cannot tell in advance how many steps it will take to reach 1, or whether it will reach 1 at all. The sequence of numbers that the rule generates seems to wander almost at random, sometimes climbing high, sometimes falling low, before eventually finding its way down to the familiar loop. There is a kind of chaos in the Collatz process, a kind of unpredictability that makes it hard to reason about. And yet, the pattern is not completely random. There is structure beneath the chaos, a structure that mathematicians have glimpsed but never fully understood. The Collatz conjecture is not the only problem of its kind. There are other simple rules that generate complex and unpredictable behavior. There are other processes that are easy to describe but hard to analyze. The Collatz conjecture is the most famous of these problems. the one that has captured the imagination of mathematicians and non-mathematicians alike. It is a problem that feels like it should have an answer, a problem that feels like it should be within reach. And yet, it remains open. As you lie there, letting these ideas settle, it is worth thinking about what it means for a problem to be both simple and difficult. The Collatz Conjecture is a problem that a child can understand, and yet it has defeated the greatest minds in mathematics for nearly a century. It is a reminder that the world is not always as simple as it seems. It is a reminder that even the most basic questions can have answers that are hidden, buried beneath layers of complexity that are not immediately visible. The Collatz Conjecture is a problem that invites you to think, to wonder, to explore. It is a problem that reminds you that there is always more to learn, always more to understand, always more to discover. The Collatz Conjecture is also connected to a broader theme in mathematics, the theme of chaos and order. The process that the conjecture describes is chaotic in some ways, but it is not purely chaotic. There is a pattern, a structure, a hidden order that mathematicians are still trying to understand. This is a theme that runs through many of the problems we have discussed tonight. The primes are scattered in a way that seems random, but they follow a deep pattern that is hidden from view. The Navier-Stokes equations describe fluid flow that can be turbulent and unpredictable, but the equations themselves are deterministic. The Collatz Conjecture is another example of this same tension, the tension between chaos and order, between the apparent randomness of a process and the hidden structure that lies beneath. So let the Collatz Conjecture be a quiet presence in your mind tonight. It is a problem about a simple rule and a simple question. It is a problem that has been open for nearly 90 years, and it will still be open tomorrow. There is no need to solve it. There is no need to understand it fully. You only need to know that it is there, that it is one of the great unsolved problems of mathematics, and that it is a reminder that even the simplest questions can have answers that are hidden, waiting to be found. That is enough. That is more than enough. Let your mind drift now from the Collatz Conjecture's simple rule to the quieter, older mysteries of prime numbers, the ones that have been waiting for an answer for centuries. There are questions about primes that are so old, so fundamental, that they feel like they should have been answered long ago. And yet, they remain open, stubbornly resisting every attempt at a solution. Two of these questions, the Goldbach conjecture and the Twin Prime Conjecture, are among the most famous unsolved problems in all of mathematics. They are simple to state, easy to understand, and they have defeated some of the greatest minds in history. The Goldbach conjecture is named after Christian Goldbach, a mathematician who lived in the 18th century. In a letter to Leonhard Euler, one of the most prolific mathematicians who has ever lived, Goldbach made a simple claim. He said that every even number greater than 2 can be written as the sum of two prime numbers. 4 is 2 plus 2, 6 is 3 plus 3, 8 is 3 plus 5, 10 is 3 plus 7 or 5 plus 5. The pattern holds for every even number that has ever been checked. Mathematicians have used computers to verify the conjecture for every even number up into the hundreds of trillions, and it has never once failed. And yet, no one has ever been able to prove that it must be true for every even number, without exception, no matter how large. The Twin Prime Conjecture is closely related. It asks whether there are infinitely many pairs of prime numbers that differ by exactly 2. 3 and 5 are twin primes. 5 and 7 are twin primes. 11 and 13 are twin primes. 17 and 19 are twin primes. The list goes on. As you travel further along the number line, twin primes become rarer, but they keep appearing. Mathematicians have checked enormous ranges of numbers and found twin primes continuing to appear, but they have not been able to prove that this continues forever. It remains possible, as far as anyone has proven, that somewhere out there, far beyond the range of numbers that have been checked, the twin primes stop appearing, that there is a largest pair of twin primes beyond which no more exist. No one has ever found such a stopping point. No one has proven that one cannot exist. These two conjectures are connected in a deep way. They are both questions about the distribution of prime numbers, about how the primes are scattered among the ordinary numbers. They are both questions that feel like they should have answers. They are both questions that have been open for centuries. The Goldbach conjecture has been open for more than 250 years. The Twin Prime Conjecture has been open for nearly that long. They are reminders that even the most basic questions about numbers can be extraordinarily difficult to answer. There has been progress on these problems, though. In the case of the Twin Prime Conjecture, a major breakthrough occurred in 2013 when a mathematician named Yitang Zhang proved that there are infinitely many pairs of primes separated by some finite gap. The gap that Zhang proved was 70 million. That is a very large gap, far larger than the gap of 2 that the conjecture asks about. But it was the first time anyone had proven that there was any finite gap that occurred infinitely often. Other mathematicians quickly built on Zhang's work, using a collaborative online project called the Polymath Project, and within months they had narrowed the gap down from 70 million to just a few hundred. The gap has since been narrowed further, but it has never been brought all the way down to 2. The Twin Prime Conjecture remains open. There has also been progress on the Goldbach conjecture. Mathematicians have proven that every sufficiently large even number can be written as the sum of 2 primes and one other number, or as the sum of a prime and a number that is almost prime. These are partial results, important but not complete. The full conjecture, the claim that every even number greater than 2 can be written as the sum of 2 primes, remains unproven. As you lie there, letting these ideas settle, it is worth thinking about what it means for a problem to be so simple to state and so difficult to solve. The Goldbach conjecture and the Twin Prime Conjecture are problems that a child can understand. They are problems that feel like they should have been solved long ago, and yet they have resisted every attempt at a solution for centuries. This is a reminder that the world of numbers is not always as simple as it seems. It is a reminder that even the most basic questions can have answers that are hidden, buried beneath layers of complexity that are not immediately visible. There is a kind of beauty in these problems, a kind of elegance that comes from their simplicity. They are problems that invite you to think, to wonder, to explore. They are problems that remind you that there is always more to learn, always more to understand, always more to discover. And they are problems that remind you that the pursuit of knowledge is not always about finding answers. Sometimes it is about sitting with the questions, letting them rest in your mind, letting them be a quiet presence in your thoughts. So let the Goldbach conjecture and the Twin Prime Conjecture be quiet presences in your mind tonight. They are problems about primes and sums and gaps. They are problems that have been open for centuries, and they will still be open tomorrow. There is no need to solve them. There is no need to understand them fully. You only need to know that they are there, that they are among the great unsolved problems of mathematics, and that they are reminders that even the simplest questions can have answers that are hidden, waiting to be found. That is enough. That is more than enough. Let your mind drift now from the ancient questions about primes and sums towards something that feels almost like a different kind of puzzle entirely. A puzzle that involves shapes and spaces and the way things fit together. There is a problem in mathematics called the kissing number problem, and it is one of those rare problems that is both easy to understand and surprisingly difficult to solve. The problem asks a simple question. If you have a central sphere and you want to place as many identical spheres around it as possible, all of them touching the central sphere without overlapping each other, what is the maximum number of spheres you can fit? In ordinary three-dimensional space, the answer is 12. You can place 12 spheres around a central sphere, each one touching it, and they will all fit snugly. If you try to add a 13th, there simply is not enough room. The spheres would have to overlap, which is not allowed. This might sound like a simple problem, and in 3 dimensions it is one that has been known for a long time. The ancient Greeks suspected the answer was 12, and they were right. But proving it rigorously took a long time. It was not until the 19th century that mathematicians were able to show, with complete certainty, that 12 is the maximum. The proof was not simple. It required careful reasoning about geometry and the way spheres can be arranged in space. But once it was done, the problem in 3 dimensions was settled. The trouble begins when you move to higher dimensions. In 4 dimensions, the kissing number is known. It is 24. In 5, 6, and 7 dimensions, the kissing numbers are known as well, but for most dimensions beyond that, the exact kissing number remains unknown. Mathematicians have found upper and lower bounds, meaning they know that the kissing number is somewhere between a certain minimum and a certain maximum, but they do not know the exact value. The gap between the upper and lower bounds narrows as mathematicians work on the problem, but it has never been completely closed. For dimensions like 8 and 24, the exact kissing numbers were found, partly because those dimensions have special symmetry properties that make the problem easier. But for most other dimensions, the problem remains open. The kissing number problem is a problem about packing, about how objects can be arranged in space without overlapping. It is part of a larger family of problems, known as packing problems, which ask how densely you can pack objects together. The most famous of these problems is the sphere packing problem, which asks how densely you can pack identical spheres in 3-dimensional space. This problem was solved in the late 1990s by a mathematician named Thomas Hales, who proved that the densest packing is the one you see when you stack oranges at a grocery store. The proof was long and complex, and it involved a significant amount of computer calculation, but it was eventually accepted as correct. The kissing number problem is a cousin of the sphere packing problem. It asks not about the density of an infinite packing, but about the arrangement of spheres around a single central sphere. As you lie there, letting these ideas settle, it is worth thinking about what it means for a problem to be both simple and difficult. The kissing number problem is a problem that you can explain to a child using a bag of oranges. It is a problem that feels like it should have a straightforward answer. And yet, in most dimensions, the answer is unknown. The problem is a reminder that even the most basic questions about shapes and spaces can be extraordinarily difficult to answer. It is a reminder that the world of geometry is full of mysteries that are still waiting to be solved. There is another problem in the same family, one that sounds almost like a joke but is entirely serious. It is called the moving sofa problem, and it asks a question that you might have encountered in your own life. If you are moving a sofa down a hallway that turns a corner, what is the largest sofa that can fit around the corner without getting stuck? The hallway has a fixed width and it turns at a right angle. The sofa is rigid, meaning you cannot bend it or take it apart. You can rotate it, you can slide it, but you cannot change its shape. The question is, what is the largest possible area that such a sofa can have? This problem has been studied for decades, and mathematicians have found some answers. They have found specific shapes that can fit around the corner, and they have proven upper limits on how large any such shape can be. The best-known shape is called the Gerver sofa, named after the mathematician who found it. It is a curved, symmetrical shape that looks a bit like a puzzle piece. It has an area of about 2.2 square units, assuming the hallway is 1 unit wide. But no one has proven that this is the absolute maximum. It is possible that there is a shape with a slightly larger area that can still fit around the corner. The gap between the best-known sofa and the proven upper limit is very small, but it has never been fully closed. The problem remains open. The moving sofa problem is a problem about geometry and motion, about the way shapes can move through space. It is a problem that has practical applications in moving furniture, but it is also a problem that is deeply mathematical. It is a problem that has attracted the attention of some of the best mathematicians in the world, and it has resisted every attempt at a complete solution. It is a reminder that even the most ordinary problems can have extraordinary depths. Let these problems be quiet presences in your mind tonight. They are problems about spheres and sofas, about packing and moving. They are problems that have been open for decades, and they will still be open tomorrow. There is no need to solve them. There is no need to understand them fully. You only need to know that they are there, that they are among the great unsolved problems of mathematics, and that they are reminders that even the simplest questions can have answers that are hidden, waiting to be found. That is enough. That is more than enough. Let your mind drift now from the playful geometry of sofas and spheres towards something that feels more solid, more permanent, like a box you might hold in your hands. There is a problem in mathematics that asks whether a certain kind of box can exist, a box with edges and diagonals that are all whole numbers. It is called the perfect cuboid problem, sometimes the perfect box problem, and it is one of those rare mathematical questions that feels almost tangible, almost like a carpentry problem, yet it has resisted solution for centuries. A cuboid is simply a rectangular box, the kind you might pack belongings into. It has 3 edges, length, width, and height. It has 3 face diagonals, the diagonal across each of its 6 rectangular faces, and it has 1 space diagonal, the long diagonal that runs from one corner of the box straight through to the opposite corner. The perfect cuboid problem asks whether there exists a rectangular box where all of these measurements, the 3 edges, the 3 face diagonals, and the single space diagonal, are all whole numbers simultaneously. No fractions, no irrational numbers, just clean, exact whole numbers. This might sound like a simple question, but it has proven to be extraordinarily difficult. Mathematicians have searched for such a box for centuries, using everything from pencil and paper to powerful computers. They have found boxes where nearly all of the measurements come out to whole numbers, leaving only 1 or 2 diagonals as irrational numbers. They have found boxes where the edges and the face diagonals are all whole numbers, but the space diagonal is not. They have found boxes where the edges and the space diagonal are whole numbers, but the face diagonals are not. They have come close, tantalizingly close, but they have never found a single example where every single measurement lines up perfectly. The perfect cuboid problem is a problem about numbers and shapes, about the relationship between the geometry of a box and the arithmetic of its measurements. It is a problem that sits at the intersection of geometry and number theory, 2 of the oldest and most fundamental branches of mathematics. It is a problem that has attracted the attention of some of the best mathematicians in history, and it has resisted every attempt at a complete solution. There is no known proof that such a box cannot exist. There is no known example of such a box either. The problem remains open, a quiet mystery sitting at the edge of what we know. There is a family of problems related to the perfect cuboid, problems about boxes and diagonals and whole numbers. The Euler brick, named after the mathematician Leonhard Euler, is a rectangular box where the edges and the face diagonals are all whole numbers. Euler bricks exist. They have been known for centuries. The question is whether there exists an Euler brick where the space diagonal is also a whole number. That would be a perfect cuboid. No one has ever found one. No one has proven that one cannot exist. There is also the rational cuboid problem, which asks whether there exists a rectangular box where all of the measurements are rational numbers, numbers that can be written as fractions. This is a closely related problem, and it has also resisted solution. Some mathematicians have shown that if a rational cuboid exists, it would have certain properties, certain constraints on its dimensions. But these constraints have never been enough to prove that such a cuboid cannot exist, or to find one that does. As you lie there, letting these ideas settle, it is worth thinking about what it means for a problem to be so concrete and yet so elusive. The perfect cuboid problem is a problem about a box, a shape you can hold in your hands. It is a problem that feels like it should have a straightforward answer, and yet it has resisted solution for centuries. This is a reminder that even the most ordinary objects can contain mysteries. It is a reminder that the world of numbers is full of surprises, full of questions that do not have easy answers. There is another problem in the same family, one that extends the idea of whole numbers and shapes into even more dimensions. The perfect cuboid problem is about a 3-dimensional box. There is also a problem about a 4-dimensional box, a hypercube, where all of the edges and diagonals are whole numbers. This problem is even more difficult, and it is even more open. Mathematicians have barely scratched the surface of these higher dimensional versions of the problem. They remain almost entirely unexplored, a vast territory of questions waiting to be asked. Let the perfect cuboid problem be a quiet presence in your mind tonight. It is a problem about a box, about edges and diagonals and whole numbers. It is a problem that has been open for centuries, and it will still be open tomorrow. There is no need to solve it. There is no need to understand it fully. You only need to know that it is there, that it is among the great unsolved problems of mathematics, and that it is a reminder that even the simplest questions can have answers that are hidden, waiting to be found. That is enough. That is more than enough. Let your mind drift now from boxes and spheres towards something that feels both ancient and modern, something that connects the earliest questions about numbers to the most current questions about computation. There is a problem in mathematics that has been hiding in plain sight for centuries, a problem about a simple operation that you can perform with a pencil and paper, a problem that has resisted every attempt at a solution for nearly 90 years. It is the Collatz Conjecture, and it is one of those rare problems that is both easy to understand and extraordinarily difficult to solve. It is a problem that has attracted the attention of some of the greatest mathematicians in history, and it has frustrated every one of them. The Collatz Conjecture is named after the German mathematician Lothar Collatz, who proposed it in 1937. The problem is simple to state. Take any whole number you like. If it is even, divide it by 2. If it is odd, multiply it by 3, and then add 1. Now take whatever number you land on and do exactly the same thing again, following the same simple rule, over and over, indefinitely. The conjecture claims that no matter which whole number you start with, this process will always, eventually, lead you to the number 1. Once you reach 1, the pattern becomes a loop. 1 is odd, so you multiply by 3 and add 1, which gives you 4. 4 is even, so you divide by 2, which gives you 2. 2 is even, so you divide by 2 again, which gives you 1. And then you are back where you started. The conjecture says that every starting number eventually falls into this loop, that no matter how far you go, no matter how large the numbers become along the way, you will always, eventually, reach 1. Try it yourself with a small number like 6. 6 is even, so you divide by 2, landing on 3. 3 is odd, so you multiply by 3 and add 1, landing on 10. 10 is even, so you divide by 2, landing on 5. 5 is odd, so you multiply by 3 and add 1, landing on 16. 16 divides down cleanly. 8, 4, 2, 1. It works. Start with 7. 7 is odd, so you multiply by 3 and add 1, landing on 22. 22 is even, so you divide by 2, landing on 11. 11 is odd, so you multiply by 3 and add 1, landing on 34. 34 is even, so you divide by 2, landing on 17. 17 is odd, so you multiply by 3 and add 1, landing on 52. 52 is even, so you divide by 2, landing on 26. 26 is even, so you divide by 2, landing on 13. 13 is odd, so you multiply by 3 and add 1, landing on 40. 40 is even, so you divide by 2, landing on 20. 20 is even, so you divide by 2, landing on 10. And from 10 you already know the path, down to 5, to 16, to 8, to 4, to 2, to 1. It works again. Mathematicians have checked this conjecture for every single whole number up into the hundreds of trillions, and it has held true every single time. They have used powerful computers to run this simple rule for starting numbers that are so large they cannot even be written down in ordinary digits, numbers with thousands of digits, and every single one of them eventually reaches 1. The evidence is overwhelming, and yet no one has been able to prove it. No one has been able to show, with the kind of rigorous logic that mathematics demands, that this process must always end at 1 for every possible starting number, no matter how large. It remains possible, as far as anyone has proven, that somewhere out there, far beyond the range of numbers that have been checked, there exists some strange starting number that either climbs upward forever, never coming back down, or that falls into a different loop, a cycle that never reaches 1. No one has ever found such a number. No one has ever proven that one cannot exist. The Collatz Conjecture is often described as a problem that is simple to state, but almost impossible to solve. It is a problem that has attracted the attention of some of the greatest mathematicians in history, and it has frustrated every one of them. There is something about the problem that resists the usual tools of mathematics. It does not seem to fit neatly into any of the established branches of the subject. It is not quite number theory, not quite analysis, not quite combinatorics. It sits in a strange, isolated corner of mathematics, and it refuses to yield to any of the standard methods. There is a reason why the Collatz conjecture is so difficult. The process it describes is deeply unpredictable. When you start with a number, you cannot tell in advance how many steps it will take to reach one, or whether it will reach one at all. The sequence of numbers that the rule generates seems to wander almost at random, sometimes climbing high, sometimes falling low, before eventually finding its way down to the familiar loop. There is a kind of chaos in the Collatz process, a kind of unpredictability that makes it hard to reason about. And yet, the pattern is not completely random. There is structure beneath the chaos, a structure that mathematicians have glimpsed but never fully understood. As you lie there, letting these ideas settle, it is worth thinking about what it means for a problem to be both simple and difficult. The Collatz conjecture is a problem that a child can understand, and yet it has defeated the greatest minds in mathematics for nearly 90 years. It is a reminder that the world is not always as simple as it seems. It is a reminder that even the most basic questions can have answers that are hidden, buried beneath layers of complexity that are not immediately visible. The Collatz conjecture is a problem that invites you to think, to wonder, to explore. It is a problem that reminds you that there is always more to learn, always more to understand, always more to explore. The Collatz conjecture is also connected to a broader theme in mathematics, the theme of chaos and order. The process that the conjecture describes is chaotic in some ways, but it is not purely chaotic. There is a pattern, a structure, a hidden order that mathematicians are still trying to understand. This is a theme that runs through many of the problems we have discussed tonight. The primes are scattered in a way that seems random, but they follow a deep pattern that is hidden from view. The Navier-Stokes equations describe fluid flow that can be turbulent and unpredictable, but the equations themselves are deterministic. The Collatz conjecture is another example of this same tension, the tension between chaos and order, between the apparent randomness of a process and the hidden structure that lies beneath. So let the Collatz conjecture be a quiet presence in your mind tonight. It is a problem about a simple rule and a simple question. It is a problem that has been open for nearly 90 years, and it will still be open tomorrow. There is no need to solve it. There is no need to understand it fully. You only need to know that it is there, that it is one of the great unsolved problems of mathematics, and that it is a reminder that even the simplest questions can have answers that are hidden, waiting to be found. That is enough. That is more than enough. Let your mind drift now from the simple rule of Collatz towards something that feels larger, more abstract, more like a question about the very shape of the mathematical universe itself. There is a problem that asks about the nature of infinity, about whether there are different sizes of infinity, and about whether there is a middle ground between the smallest infinity and the next one up. This is the Continuum Hypothesis, and it is one of the most famous unsolved problems in the history of mathematics. It was first posed by Georg Cantor in the late 19th century, and it remained open for decades, resisting every attempt at a solution. In the 1960s, a mathematician named Paul Cohen proved that the Continuum Hypothesis is independent of the standard axioms of mathematics, meaning that it can be neither proven nor disproven using those axioms. This was a profound result, one that showed that there are questions in mathematics that do not have a single, fixed answer, but that depend on the assumptions you choose to make. To understand the Continuum Hypothesis, you first need to understand what Cantor discovered about infinity. Before Cantor, infinity was treated as a single, vague concept, a word that meant simply without end. But Cantor showed that infinity is not one thing. There are different sizes of infinity. The infinite collection of all whole numbers, for example, is smaller than the infinite collection of all points along a continuous line. This was a shocking idea at the time, and it provoked fierce resistance from some of Cantor's contemporaries. They could not accept that there could be different kinds of infinity, that something as abstract and unbounded as infinity could be measured and compared. But Cantor's arguments were rigorous, and his ideas eventually became accepted as central to modern mathematics. Cantor then asked a natural question. Is there an infinity that sits strictly between the size of the whole numbers and the size of the continuous line, or are those two particular infinities directly adjacent to one another, with nothing possible in between? This became known as the Continuum Hypothesis. Cantor suspected that the answer was no, that there was no intermediate infinity, but he could not prove it. The problem remained open for decades, and it became one of the most famous unsolved problems in mathematics. It was placed at the top of David Hilbert's list of 23 unsolved problems, delivered in 1900, as the very first and most important open question facing mathematics at the dawn of the 20th century. The Continuum Hypothesis resisted every attempt at a solution for more than 60 years. Then, in the 1960s, Paul Cohen proved something that no one had expected. He showed that the Continuum Hypothesis is independent of the standard axioms of set theory. This means that it can be neither proven nor disproven using the accepted rules of mathematics. The Continuum Hypothesis is not a question with a hidden answer waiting to be found. It is a question that sits at a genuine fork in the road. You can choose to add the Continuum Hypothesis to your axioms, and you will have one kind of mathematics. You can choose to add its negation, and you will have a different kind of mathematics. Both choices are equally consistent with the standard axioms. The Continuum Hypothesis is not a problem to be solved. It is a choice to be made. This is a strange and unsettling idea, and it takes time to settle in. It means that there are questions in mathematics that do not have a single, fixed answer. It means that the mathematical universe is not a single, monolithic structure, but a landscape with multiple possible paths. It means that the truth of a mathematical statement can depend on the assumptions you choose to make, and that there is no single, privileged set of assumptions that is guaranteed to be correct. This is not a failure of mathematics. It is a feature of the landscape, a reminder that the world of mathematics is richer and more complex than anyone had previously imagined. As you lie there, letting these ideas settle, it is worth thinking about what it means for a question to be independent of the axioms. It means that the question is not settled by the rules of mathematics alone. It requires an extra assumption, a choice that the mathematician must make. This is similar to the choice that ancient geometers faced when they considered the parallel postulate. For centuries, mathematicians tried to prove the parallel postulate from the other axioms of geometry, and they failed. Eventually, they realized that the parallel postulate was independent of the other axioms, and that you could choose to accept it or reject it. If you accepted it, you got Euclidean geometry. If you rejected it, you got non-Euclidean geometry. Both systems were equally valid, equally consistent, equally useful for different purposes. The Continuum Hypothesis is like the parallel postulate. It is a choice, not a fact. The independence of the Continuum Hypothesis is a reminder that mathematics is not a single, fixed body of knowledge. It is a living, growing enterprise, one that is shaped by the choices that mathematicians make. It is a reminder that there is no single, final, complete system of mathematics, no set of axioms that can capture every truth and settle every question. This is a humbling thought, but it is also a liberating one. It means that mathematics is not a closed system. It is an open field full of possibilities, full of choices, full of questions that are waiting to be asked. The Continuum Hypothesis is not the only independent statement in mathematics. There are others, and they are part of a larger family of questions about the foundations of set theory. These questions are about the nature of infinity, about the structure of the mathematical universe, about the limits of what can be proven. They are questions that are still being explored, and they are questions that may never have a single, definitive answer. They are reminders that the mathematical universe is vast, complex, and full of mysteries. Let the Continuum Hypothesis be a quiet presence in your mind tonight. It is a problem about infinity and choice. It is a problem that has been shown to be independent of the standard axioms, a problem that sits at a fork in the road. It is a reminder that mathematics is not a single, fixed body of knowledge, but a living, growing enterprise, one that is shaped by the choices that mathematicians make. There is no need to solve it. There is no need to understand it fully. You only need to know that it is there, that it is one of the great unsolved questions of mathematics, and that it is a reminder that the mathematical universe is vast, complex, and full of possibilities. That is enough. That is more than enough. Let your mind drift now toward the quiet edges of what we have explored tonight, toward the place where the great questions of mathematics live alongside the ordinary moments of your life. There is something worth holding on to as you lie here in the dark, something that connects all of these ideas to the world around you, to the phone on your nightstand, to the blood moving through your body, to the air in your room. The unsolved problems of mathematics are not distant abstractions, locked away in ivory towers. They are woven into the fabric of your daily life, quietly underpinning the technology you use, the buildings you enter, the very atoms that make up your being. And yet, despite their importance, they remain unfinished, unresolved, waiting for someone to see them clearly enough to close the gap. The security protecting your phone, your bank account, your private messages, rests on a mathematical gap that has never been formally proven to be permanent. The encryption that guards your digital life is built on the assumption that factoring large numbers into their prime components is hard. This assumption has held up for decades, against the efforts of some of the brightest minds in the world. But it is still an assumption. It has never been proven. If someone found a fast way to factor large numbers, the security of the modern internet would unravel. This is not a distant possibility. It is a real, present uncertainty, one that cryptographers take seriously every single day. They build new systems, new algorithms, new ways of protecting information, always aware that the foundation they stand on is not fully secure. The equations that describe the flow of fluids, the Navier-Stokes equations, are running through the software that predicts tomorrow's weather, the designs of the airplanes that carry millions of people, the models of blood flow that help doctors understand the human body. These equations work. They are reliable in practice, but no one has proven that they always work, that they never break down, that there is no hidden mathematical catastrophe lurking in some extreme condition. Engineers trust them because they have been tested again and again, and they have never failed. But trust is not proof. The gap remains. Prime numbers, the same objects Euclid studied more than 2,000 years ago, are the foundation of the encrypted connections your phone uses to load websites and send messages. Large primes are multiplied together to create mathematical locks, and the difficulty of breaking those locks is the bedrock of digital security. The Riemann Hypothesis, if proven, would deepen our understanding of how primes are distributed, but it would not necessarily break encryption. It would, however, touch nearly every corner of modern number theory, including the tools cryptographers rely on. It remains unproven. There is a current development worth thinking about, one that has kept cryptographers and computer scientists on edge for years. In 1994, a mathematician named Peter Shor showed that a sufficiently powerful quantum computer could factor large numbers dramatically faster than any known method running on an ordinary computer. This would break the encryption that protects most of the internet. Quantum computers capable of doing this do not yet exist, but the theoretical possibility has already pushed researchers to develop new encryption methods, ones that would resist even a quantum computer's abilities. This is a quiet arms race, unfolding in research labs around the world, while you lie here in the dark. Even the physics of your own body connects to these unsolved problems. The protons and neutrons in every atom of your body are held together by the strong force, described by Yang-Mills theory. The reason those particles have mass, the reason they exist at all, is tied to a mathematical gap that has never been closed. You are made of matter whose most basic properties rest on an unproven foundation, and yet you exist, steadily and reliably, without needing the proof to be written down. There is more. Scattered through the ordinary machinery of daily life, the images from medical scans, MRIs, and CT scans are reconstructed using mathematical techniques that trace back to the same family of ideas that Riemann and Hodge worked on. The GPS system that guides your phone and your car relies on precise timing from satellites, timing that must account for effects predicted by Einstein's general relativity, a theory built on the curved space mathematics Riemann developed in the 1850s. Even cryptocurrency depends on the practical difficulty of certain mathematical problems, using puzzles that are hard to solve but easy to verify. None of these systems require the underlying open questions to be resolved. They run on a foundation of overwhelming empirical confidence, layered directly on top of gaps that remain technically open. Now let us spend a little while on the harder questions, the parts of this whole picture that mathematicians themselves still find strange. The most unsettling question, hovering quietly behind every problem we have discussed, comes from Gödel's incompleteness theorems. If some true statements can never be proven at all, how would anyone ever know whether the Riemann hypothesis, or the Twin Prime Conjecture, or any of these other unsolved problems belongs to the category of statements that are simply waiting for a clever proof, or whether it instead belongs to the much stranger category of statements that are true but can never be proven? There is no reliable way to know in advance. This is a genuine uncertainty, built into the structure of logic itself. There is also the mystery of where mathematical insight comes from, before any formal proof is ever written down. Srinivasa Ramanujan, largely self-taught, working in isolation in southern India, filled notebooks with thousands of formulas and identities, many of which, by his own account, came to him in dreams or moments of quiet reflection. When he sent a selection to the Cambridge mathematician G.H. Hardy, Hardy was stunned by their depth and strangeness. Ramanujan was brought to Cambridge, where he and Hardy collaborated for several productive years before Ramanujan's health failed, and he died at only 32. More than a century later, mathematicians are still working through Ramanujan's notebooks, finding formulas that later turn out to be entirely correct, and occasionally connected to areas of modern mathematics that did not exist during his lifetime. His story is a reminder that mathematical truth and mathematical proof, while closely related, are not quite the same thing. A mind can sometimes sense a true pattern with real confidence, long before anyone can fully explain why it must be true. Some mathematicians have wondered whether certain famous open problems might turn out to be genuinely unprovable, a possibility that can never be fully ruled out in advance, precisely because Gödel showed that unprovable truths must exist somewhere, even though his proof does not tell us exactly which specific statements they are. There is also a long-running philosophical debate about what mathematical truth actually is. Some mathematicians, following a view called Platonism, believe that mathematical objects, numbers, shapes, the primes, the zeros of Riemann's zeta function, exist in some real, independent sense, out there somewhere, waiting to be noticed. Under this view, an unsolved problem like the Riemann hypothesis has a definite, fixed answer already, true or false, sitting there in whatever sense mathematical truth can be said to sit anywhere. Other mathematicians, following a more formalist view, believe mathematics is best understood as an elaborate, self-consistent game, played with symbols and agreed-upon rules, a powerful and useful game, but not necessarily describing some independently existing reality. This debate has never been definitively settled, and it probably never fully will be. The story of the ABC conjecture and Shinichi Mochizuki's disputed proof raises a related question. Some proofs are now so complex, so long, and built using such unusual frameworks that only a small handful of people on the entire planet are capable of reading through them carefully enough to verify whether they are correct. If only 3 or 4 people in the world genuinely understand a certain proof well enough to verify it, and they happen to disagree among themselves about whether it is actually correct, what does it even mean to say a problem has or has not been solved? This is not an abstract worry. It is playing out, quietly and genuinely, right now, in the ongoing disagreement over Mochizuki's proof. There is a related question, one that comes from a problem that was solved in a way that made many mathematicians uneasy. The four-color theorem, first proposed in the 1850s, claims that any map can be colored with only 4 colors, so that no 2 neighboring regions share the same color. In 1976, 2 mathematicians produced a proof that relied heavily on a computer to check nearly 2,000 specific configurations. The proof was accepted as correct, but its reliance on a computer performing an enormous number of individual checks made many mathematicians uneasy. Part of what a mathematical proof has traditionally offered is not just certainty, but also genuine human understanding, an insight a person can actually hold in their mind and follow step by step. A computer-assisted proof can sometimes deliver the certainty without quite delivering that same feeling of understanding. Mathematicians still debate how much that distinction ought to matter, and there is one more gently unsettling question worth sitting with. Throughout history, mathematicians have occasionally discovered that certain seemingly reasonable, well-posed questions turn out to have no answer at all, not because nobody has found the answer yet, but because the question itself was subtly flawed from the very beginning, built on some hidden assumption that does not actually hold. Set theory contains modern examples of statements that have actually been proven to be entirely independent of the standard axioms, meaning they can neither be proven true nor proven false, and mathematicians are free to simply choose which answer they prefer. This raises the quiet possibility that some of tonight's unsolved problems might, eventually, turn out to belong to this same strange category. Let us gather up, gently, everything we have walked through tonight. We began with Euclid, more than 2,000 years ago, proving that prime numbers never end, a proof so solid it has never needed revisiting since. We watched that same question about primes deepen into Gauss's careful guess about how densely they are scattered, and then deepen further still through Riemann's strange and beautiful discovery that the scattering of primes is secretly written into the zeros of a function nobody had previously connected to prime numbers at all. We saw an entirely different kind of question emerge, about whether any fixed set of rules could ever capture every mathematical truth, and we watched Gödel and Turing show that it cannot, that truth will always outrun the reach of any single, fixed system of proof. We watched that same insight about mechanical limits reappear inside the ancient equations of Diophantus, inside the practical difficulty of planning a delivery route or breaking an encrypted message, inside the physical behavior of water and air, inside the invisible force holding every atomic nucleus in your body together, and inside the layered, curved shapes of algebraic geometry that resist being pictured at all. We picked up smaller, stranger threads too, spheres kissing each other in dimensions nobody can see, a sofa turning an impossible corner, a box whose diagonals refuse to line up, primes hiding at the far edge of what any computer has ever managed to check. If you were to hold all of tonight in one single image, it would be this. Picture an enormous, quiet library, far larger than any library that has ever physically existed, containing every true mathematical statement there could ever possibly be. Some sections of this library are fully lit, catalogued in perfect and complete detail, filled with statements that have been proven true beyond any possible doubt. Other sections sit in a kind of dim, flickering half-light, where mathematicians have gathered overwhelming evidence, and yet the final light has never quite switched fully on. And Gödel's incompleteness theorem tells us that this library will always contain at least a few statements that can never be lit, not because nobody has looked there yet, but because the light itself, the very concept of proof, simply cannot reach that particular section. And yet, none of this uncertainty has ever actually stopped the library from being useful, or beautiful, or worth exploring further. Engineers build airplanes using approximate versions of equations whose deepest mathematical properties remain formally unproven, and those airplanes fly safely, carrying millions of people every single day. Your phone protects your private messages using a mathematical gap that has never been formally certified as permanent, and yet it has held up reliably, every single day, for decades. Mathematicians continue devoting entire careers to problems they may never see solved within their own lifetimes, the way generations before Perelman spent their careers building the groundwork he would eventually complete. The not knowing has never actually been the obstacle it might initially seem like. It is simply the honest, quiet, ongoing condition of exploring a library this large, one careful room at a time, generation after generation. So here, at the end of tonight, is where we return to where we began. Your phone, resting somewhere nearby right now, in the dark, quiet room around you, is still holding its secure lock, exactly the same way it was at the very start of tonight's explanation, using a gap in mathematical knowledge that has never been formally closed. The atoms making up your own body are still held together by the same unproven mass gap, quietly, reliably doing their job regardless of whether anyone has ever written down the full mathematical proof underneath them. The blood is still moving through your body according to a set of equations that engineers trust completely for every practical purpose, even though mathematicians still cannot fully certify, in every conceivable case, that those equations will always behave the way we expect them to. None of this uncertainty has ever once gotten in the way of any of it actually working, steadily, quietly, all around you and inside you, every single night, including this one. Think for just a moment longer of Wiles, working quietly in his attic for 7 years, telling almost nobody what he was actually doing, simply trusting that the work itself was worth the isolation. Think of Perelman, finishing one of the greatest proofs of the last century, and then walking away from the prizes entirely, content to let the mathematics speak for itself. Think of Zhang, teaching introductory classes for years in relative obscurity, before quietly finishing a proof that had waited for a solution since Euclid first noticed primes clustering together. None of them knew, while they were doing the actual work, exactly how or when their particular piece of understanding would arrive, or whether it ever would at all. They simply kept going, patiently, one careful step at a time, the same way you are allowed to simply keep resting now, one breath at a time, without needing to know exactly when sleep will actually arrive. Somewhere out past the edge of what anyone has proven, the primes are still following whatever quiet rhythm Riemann first sensed in 1859, still scattering themselves through the vast, unending field of numbers, indifferent to whether the proof ever gets written down. The equations describing the air in your room and the blood moving quietly through your body are still behaving exactly the way they always have, needing no permission from any mathematician to keep doing so. And the space around you, wherever you are lying right now, in the dark, at whatever hour this happens to be reaching you, is exactly as full of unfinished, unproven, and entirely trustworthy mathematics as it was at the very start of tonight. There is something quietly comforting, if you let yourself sit with it for a moment, in the fact that the universe runs perfectly well on top of mathematics that nobody has fully finished explaining yet, and that we, in turn, can rest just as easily, right now, tonight, on top of ideas we may only be half following, drifting somewhere between waking and sleep, without needing the whole picture fully lit before we are allowed to let go and rest.